You can have so much data that you don't even know where to begin and you don't know how to sort through it to get useful insights, which is the whole point of getting data in the first place. And this is where we turn to data mining. I'm Barton Poulson, and in this course, you'll see how you can quickly use both simple and sophisticated methods to get a better understanding of how to mine data for value and, in turn, reach the goals that are important to you. And with that, let's get started with Data Science Foundations Data Mining with Python. While this course is designed as an accessible introduction to the field of data mining, it works best if there are a few things you already know. The first thing is that you should already be familiar with the Python programming language and the Jupyter notebooks in the Anaconda environment. If you'd like some help getting up to speed on those, I recommend that you take a look at the course Introducing Jupyter, as well as Python for Data Science Essential Training Parts 1 and 2. In addition, it's helpful if you're familiar with basic statistical concepts. If you'd like a refresher, I'd recommend the course Data Fluency, Exploring and Describing Data, as well as several other courses available in our online learning library. If you have access to the exercise files for this course, then you can download them to your desktop, as I've done here. When you open the exercise files folder, you'll see that it has the Python scripts with the .ipynb extension. That's for IPython Notebook. That's what's used in Jupyter notebooks that are included in the Anaconda distribution of Python that we'll use. In addition, there is a data folder that contains the CSV files and text files with the datasets that we'll use for these demonstrations and challenges. If you don't have access to the exercise files, that's okay. You can still follow along by watching how I use the course files. If you're going to go out mining, then you need the right tools. When you're mining for data gold, that means software. And the two most common tools for that are Python and R. Now, as it happens, we have two versions of this course, with one showing how to mine data in Python and the other one in R. There are good reasons for choosing these two languages. Python is currently the most popular language for data science and machine learning. It has an advantage of being a general purpose language, which means millions of people know how to use it because it can program basically anything. It's also well adapted for data. Python also is really easy to learn. It's got a clean, readable syntax. R is a different kind of language. It's a programming language that's specifically developed for data analysis. Consequently, it's very popular with scientists and researchers. So it's what I learned first as a way of working with data. Either one works great for mining data, but I do want you to be aware of some of the other options. I want to make sure to mention applications with point-and-click GUIs, or graphical user interfaces, that are developed with data work in mind. Some of these are free, some are expensive, some are similar to spreadsheets, some have extensive programming abilities. They include apps like SPSS, very popular for analyzing data in the social sciences, which is where it was first developed. Or SAS, which also has strong programming abilities. Jamovi, a free open source application that resembles SPSS but runs on R, is one of my personal favorites. JASP is another free open source application that strongly resembles SPSS and Jamovi. And then there's Tableau, which is specifically for data visualization, but it's one of the go-to tools for people who are trying to get a feel for large data sets. In addition to these apps, one language that anybody who's going to work with data should learn is SQL. That's Structured Query Language, and it's usually pronounced SQL. This is for accessing databases, and especially if you're working in a large organizational setting, you're going to have a lot of data in databases. SQL has a great learning ROI, or return on investment. It doesn't take much to get most of the things that you're going to need in SQL and get ready accessing and cleaning and querying data. I also want to mention spreadsheets. So the rows and columns of Microsoft Excel and Google Sheets. The reason these are important is A, they're the single most common data tools in the world. That's my personal belief. Everybody has them, and a good chance is if you're working with a client, they may provide you with data in spreadsheets. They may want the results back. They're great for browsing data. They're great for making very simple graphs. And anybody who's going to work with data owes it to themselves to be very comfortable with both of these spreadsheets. Now, I want to give you my personal philosophy about data tools. I see an order to things. Generally, I recommend that people start with the simplest tools, and that would be spreadsheets, until the data you're working with or the analyses you need to do become unwieldy. Then consider the next step up. That's an application like Jamovi or SPSS. These allow you to do a lot of specialized procedures for analyzing and mining data, or use a data mining specific application like RapidMiner or KNIME. But only then should you consider taking the final step to programming languages. They are, of course, the most flexible and powerful, but often they're also the most difficult to learn and to use proficiently. I do want to give you a little bit of data about programming languages and apps for context. KD Nuggets is one of the most common and popular sites for information about data mining. KD stands for Knowledge Discovery, and this is their most recent survey of software use among practicing data miners. And what you'll see here is that Python is number one on the list, where 66% of the respondents said that they use Python on a regular basis. 51% said they used a software application called RapidMiner. And, it's popular, but the survey people say that may have been because the survey was actively promoted on a RapidMiner discussion list. R is third at 47. Please note that Excel, the spreadsheet, is here at 35. Anaconda is really a distribution of Python. And then there's the language SQL here at the end. So it lets you know some of the things that are frequently used in data mining. Another perspective on this is postings for data science jobs on the job site Indeed. And this is from 2017, so it's a little old, but the pattern is consistent over time. What you see again is Python is here at the top. SQL is close behind. It is still an important thing in data science. Then if you come down here, you'll see that R is still in demand. Any one of these can be very useful tools for data mining. And so consequently, I want you to choose your tools wisely. You have great flexibility and choices. I'm going to be emphasizing Python and R in the two versions of this data mining course, but you have a lot of other options. Almost any tool you can choose can do almost any analysis if you give it enough work. But do some things. Look at the client's requirements. Do they use a particular software application or language that they want you to use? Obviously, you'd want to work with that. Python and R are common, but use what works best for you and the particular project you're working on, and that can get you started on getting some insight from your data as you mine through it for the valuable insights. I know this course focuses substantially on how to program analyses to mine data, but it also is important to think about the context in which that programming takes place. That is, the project as a whole. And when it comes to data mining, there is in fact a well-established framework for projects. It's called CRISP-DM, and that stands for Cross-Industry Standard Process for Data Mining. And it describes 6 phases to data mining. I'll give you a quick overview of each of these. The first phase is business understanding. This is where you do things like determine the business objectives, the thing you're trying to accomplish, the situation assessment, determine data mining goals, and produce the project plan. The second phase is data understanding. This is where you collect the initial data, you describe the data, explore the data, verify the data quality. The third phase is data preparation. This includes describing the data set, selecting the data, including the rationale for including or excluding particular cases, cleaning the data, constructing the data, which means things like derived attributes and generated records, and then integrate the data, so merging it with other sources, and then formatting the data to make it so it fits with the existing data and so it fits the software that you're going to be using. The fourth phase in CRISP-DM is modeling. This is where you select the modeling technique and check the assumptions, generate the test design, build the model, including looking at parameter settings, the model description. Then you can assess the model. That's looking at things like how well does it fit the data, and do you need to revise any of the parameters that you used? The fifth phase is evaluation. This is where you can evaluate the results, see how well the results work with regards to the business success criteria, and then you can review the process, determine the next steps. That's a list of possible actions or perhaps a final decision. And then the sixth and final phase of CRISP DM is deployment, where you apply the conclusions to the problem to be solved, the reason you designed the project in the first place. So this includes plan deployment and plan monitoring and maintenance, see how well it holds out, producing the final report or presentation, and reviewing the project, including the documentation of the entire process so it can be evaluated and possibly replicated in the future. So that is CRISP DM, one of the most common process descriptions for data mining. If you'd like another take on the organization of a data project, I've described my own personal system, which I call the Data Science Pathway, in the course Data Science Foundations Fundamentals. But with either approach, the industry standard CRISP DM or the Data Science Pathway, you're going to be better able to set up, run, and get actionable insights from your data mining projects. I know we're here for some technical training, but I want to take a minute and remind you that data mining, like basically everything else, takes place in a human, social context. It's important to respect the people who provided the data or who will benefit from your work. And there are a few important dimensions to that respect. The first important issue is privacy, which affects how you gather data, how you store data, and what you share. This is both an issue of good manners and, as it happens, several major laws. For instance, in the European Union, there's the GDPR, that's the General Data Protection Regulation. In California, there is the California Consumer Privacy Act, or CCPA. In the US, there's also at the federal level, HIPAA, the Health Insurance Portability and Accountability Act, which is going to affect health records. And then there's FERPA. This is the U.S. Family Educational Rights and Privacy Act. So if you're working with any educational data, this is another important set of regulations you're going to have to work with. And all of these are regulations that have teeth. They are very specific about some of the things that you can use, what you can't use, or how you have to process the data to meet privacy regulations. And there's a lot more details on each of these. But if you're working with data from the European Union or in California, or health records or education, you owe it to yourselves to take a little bit of time to see how each of these regulations deal with privacy. There's also copyright. And this is important because data mining often uses data that's found on the web. And you know how you can't, for instance, just use any picture or video you find online because they may still belong to the people who created them. You need to have the proper license. Now, it may be that they put a Creative Commons license on there and make it so anybody can use it, but it may be restricted and proprietary, in which case you need permission or possibly to pay a fee. The same thing is true of data. You can't assume that data can be freely used just because it's on the web. Just because you see the numbers in front of you doesn't mean you can take them. That data belongs to somebody. They put it there, and you have to check the license to make sure that what you're doing is permissible. And then there's the issue of whether your data is potentially biased. And I think of a few elements in this. Number one, anybody who's worked in computer programming knows GIGO, which stands for garbage in, garbage out. And what that means is if you have bad data, well, you may have a great algorithm, but if you start with bad data, you're going to end up with bad conclusions, even if you have very sophisticated approaches. So you need to check the quality of your data before going in. And that includes the representativeness. Specifically, do you have a sufficiently diverse data set that the data set that you train your model on matches the data that will be coming in once you put your model out there in the wild? So you want to look at the diversity, the spread, both of people and of situations, and the weighting, how much emphasis you put on each kind of case in your training sets so it can transfer well to the testing data. And then there's an issue of construct validity. And that really means, are you measuring what you think you're measuring? And it has to do with interpretation because there's often a gap or at least a slight mismatch between what you want and what you have, especially in data mining, because you're frequently using what's already there. And so it's very important to interpret things in the most precise manner that reflects what it actually meant when the data was gathered. Now, if you want more information on some of these privacy issues and social issues, you can take a look at another course, AI Accountability Essential Training, which is available here, which goes into all of these issues in more depth and will make it so you can construct, plan, conduct, and implement your data mining project while getting more meaningful and accurate data and avoiding some common pitfalls. Here where I live in Utah, I can see the world's largest copper mine from my kitchen window. Actually, you can see the Bingham Canyon mine, better known as the Kennecott copper mine, from pretty much anywhere in Salt Lake County. I mean, it's several miles across. You can even see it from a NASA satellite photo like this one. Now, mining is hard. If the things you wanted were sitting there right on top of the ground like watermelons, you wouldn't have to dig up so much dirt to get the valuable things that are hidden. The same thing is true in data mining, except now instead of looking for copper, we're looking to find the signal that's hidden in the noise of the data. We're trying to find the meaningful and actionable patterns in the randomness. But there are a few things you need to be aware of. And one of the most important is that with enough parameters, with a sufficiently complicated model, your model can fit any data set perfectly, but that doesn't mean it's going to work well in practice. This is known as the danger of overfitting, getting a model that is much too specific to the data that you currently have. The problem is that when a model is too closely meshed to the data, it doesn't work well with new data. This issue can go by several names. You can call it statistical model validation. You build a model on your sample data or your training data, but is it valid? Does it work well with the testing data or with new data? In some circumstances, it's called external validity. How well does your model work when you go out the door from your lab to the real world? And then there's the catch-all term of generalizability. How well does your model, the thing that you did all this work in data mining for, how well does that work with new people? The enormous variety that you can encounter, for example, when you launch a new social platform. Now, these are important issues. Fortunately, there are several ways to assess the validity of your model to try to estimate how well it's going to work when you go beyond the data that you built the model on. The standard method from laboratory sciences like the one I'm trained in is usually done manually and in great detail. It says, check the data. So you're actually going to do a hands-on verification of the distributions, whether you have outliers, whether you have anomalies. Then you might check the fit. How well does your data match the assumptions of your statistical procedures? How well do the data fit the particular model? Then you can check the sample. You're going to look at it more closely. Does it appear to be representative of the overall population? Are there unusual cases of missingness in the data? And then when you're all done with that, you just do the study, get more data, do it again. Now, you can think about validation happening at 2 points in time. The standard model that I just described assumes that validation happens in the future. So you do the study again with a new sample. This is replication. And maybe you'll do it in a different place or maybe with a slightly different method. And when you're done, you can combine the results or at least compare them to see how consistent they are over time. On the other hand, you might want to do things right now. With enough data, you can do replications with what you currently have. And there are a few general ways that this is done. One is referred to as holdout validations, and the other is referred to as cross-validation. I'll describe each of these. With holdout validation, what you do is you split the data set into 2 parts. One is called a training data set, and that might be 70% of the data. Sometimes it's 80, sometimes it's 90. And the other part is the testing data set, and that's the rest of the data. And the idea here is that you train the model, you build your model, you do all your mining on the first part, the training data set. And then once you've come up with a really good model that you're confident in, you test that model on the second part. The idea is you only touch the second part once. You do all of your work, all of your evaluations on the training data set. And sometimes you can have a third part that goes in between called a validation data set, which lets you compare several different methods that you're exploring and evaluate them on another data set, and then pick the best one and apply it to the testing data set. Now, I'll use this method in many of the demonstrations in this course, but I also want you to be aware of cross-validation. And this is where you split your data set into K folds or segments. K is a number that you choose, and it might be, for instance, 3, 5, 10, 20. And the idea here is that you take all of the parts except one. You take K minus 1 parts and you train the model on those, and then you test the model on the remaining fold. And then you rotate through the data set K times, so each fold can serve as a test set. You can think of it this way. Cross-validate many models on 60% of your data, or maybe it's 50%, or maybe it's 80, some percentage. And then you validate the model on 20%, but you rotate through and you try it again each time. And then you find a good model, the best one, and you test that on the last 20%. And I will demonstrate this approach with a few of the procedures that we have in this course. The idea here is that all of your work in data mining, that's the digging, the sorting, and the sifting through the data and the models, allows you to find the greatest value. And then these validation methods allow you to verify your findings and proceed to implementation with confidence. Data mining comes into its own when you're dealing with lots of data. You may be familiar with the 3 V's that define big data: volume, velocity, and variety of the data. But it turns out that paradoxically, you can have too much of a good thing. Having lots of cases or observations is generally good, but things get much more complicated when you have many, many dimensions or fields or features or variables. And there are a few reasons why that can be a special challenge. Some of the problems that come up with high dimensionality include an exponentially increasing complexity and demands. You have so many more possibilities now, and it becomes so much harder to compute it. That's because each dimension isn't additive, it's multiplicative. Also, with each variable, you have idiosyncratic error. That means each variable doesn't perfectly represent the thing that you're hoping that it measures. It represents something close to it, but it brings in its own little bit of noise. And when you have lots of different noise, it becomes harder to find the signal in the data. And consequently, you also have the risk of overfitting. If you have 1,000 variables in there, and just at random 17 of them are super correlated with your outcome, your algorithm's going to latch onto those. But if those 17 variables are affected by noise, it's not going to generalize well when you go to another situation. And finally, when you have a lot of variables or dimensions, you have issues with interpretability. If you're building a model that a human has to understand, and it's got 700 variables that interact in very complex ways, it's nearly impossible to make heads or tails of it for human-driven decision-making. And so there are some solutions to these particular problems. One is to combine variables to reduce the complexity or dimensionality of your data set. One interesting thing about this is, in general, the errors associated with each variable tend to cancel out when those variables are combined. This gives you more stable measurement and gives you better generalization of your model from the current data to conceivable new data. Also, because you now have a smaller number of dimensions that you're dealing with, it may be easier to interpret the model and have human decision makers apply it in their processes. The general concept we're dealing with here is dimensionality reduction, or fewer dimensions. And the idea is to project the data into a lower dimensional space while preserving as much as the useful variability and interrelationships as possible. There are a couple of metaphors for this. One is to think of a hand's shadow. A hand is a three-dimensional object, but a shadow is two dimensions. Now, depending on the position of the hand, the light source, and the surface, you can get a shadow that might be a little bit ambiguous like we have here on the left, but the shadow on the right is readily identifiable as a hand, even though you've lost one of the dimensions in the process. A similar process can happen with data, and you can get the data shadow as a way of thinking about it. For example, a scatter plot like this shows a two-dimensional representation. We got our variable x across the bottom, our variable y up the side, and each dot represents a pair of values for each case. So we have two dimensions. Now, you can see here on the vertical dimension, we've got a fair amount of variability. It goes from -4 to +4. And we have the same thing on the horizontal. It goes from -4 to +4. And so we have two distinct dimensions. But if we were to rotate the plot so it goes on this regression line that's in the middle, then we have almost no vertical variability, and we have enhanced variability on the horizontal axis. And at this point, instead of talking about two dimensions, we can talk about a single common component or dimension, and it makes it much easier to deal with the data. Now, there are many choices, many algorithms for dimensionality reduction, but there are three I want to show you in this course. The first one is PCA, which stands for Principal Component Analysis. It's far and wide the most common method, along with the closely related factor analysis. And what PCA does is it looks for components, those are like combined dimensions, that can account for several factors or variables at once, the same way we rotated the scatter plot and then we saw one clear dimension that we could use instead of two. That actually shows you that the rotation is an important part of the interpretation and implementation of PCA. Another method that we're going to look at is LDA, which stands for Linear Discriminant Analysis. And what this does is it's designed to separate cases or your observations into different classes or categories. So it's actually a method of classification, but it uses these underlying components to do it. It combines the variables in the data set into dimensions that can separate the classes cleanly. And then a particularly sophisticated method is TSNE, which is short for T-distributed stochastic neighbor embedding. This is an example of a non-linear dimension reduction, and it's good for showing probabilities of pairs being connected in points. And if you have data that's arranged in a helix like this one, or you have circles or one's enclosed in the other, then TSNE can be a very powerful method for finding the dimensions even when you can't draw a straight line between things. Any one of these methods, PCA, LDA, TSNE, and many, many others, can be ways to help you sort through a very large number of dimensions or variables in your data set and combine them into smaller, more stable, and more generalizable factors or components that can help you more easily find the value in your data. And let me show you how this works in Python. Now, when we open up Python, I just want to point out one thing before I get started. You usually see it in a browser window if you're using Jupyter and the Anaconda distribution, and you have the menu bars from your web browser. I'm going to do two things to make the demonstrations work a little better. First off, I'm going to switch my browser to full screen. Then in the Jupyter interface, there's a few other things I can do. I can come to view and I can toggle the header, that's the top there, and I can also toggle this toolbar. This gets me to the minimalist version of the Jupyter interface, and it's the one that is best for these demonstrations, so it's what I'm going to be using throughout the course. Just be aware that you can bring back the toolbars, you can bring back the browser menus if you want. But back to the handwritten digits dataset. To do this, I'm first going to load several libraries and functions. And then I'm going to come down and load the data set. Now, I've saved this as a local CSV file to make it much easier to deal with, and it's in the data folder for our course. So I'm going to open this data file. You can read it directly from the University of California at Irvine Machine Learning Repository if you want. Just uncomment these 3 lines, run that one. You'll get the exact same thing. But let's take a look at the data very quickly. And what we have are 5 rows of data here, 0 through 4. And then we have numbered columns. These are the pixel data here. And then the very last one is the class identifier. So let's rename these columns so they're a little more informative. What I'm going to do is I'm going to take the attributes, the ones that tell us how many pixels there are in a particular part of the image, and I'm going to rename them starting with P for pixels. And then the last one, a lowercase y, which is what I just call a class or outcome variable, unless I have a reason to use something else. So I run this command. And then also the data set includes the numbers 0 through 9, and that makes sense. But to make our demonstration work a little faster, I'm going to restrict it to just the numbers 1, 3, and 6. So this command will restrict it to those numbers, and we'll take a look at the first few rows. And here you can see we have rows 4, 11, 14, because these are the ones that have the 6, the 1, or the 3 in them. And so this is the data set that we're going to be working with. There is, however, one additional step we need to take, and that's because we're using machine learning algorithms, and it's most common in these situations to do a training data set and a testing data set. We have a large data set, so we can make that split. I'll be using the train test split function and creating the X train and Y train and X test and Y test data sets. This will split it up the way that we need. And now we can begin exploring the training data set. That's the one we're supposed to be working with as though it's the only one we know, and then we later go to the testing. Let's start by looking at the first 20 images that are in the training data set. So this will set up a grid for the images, and then it'll actually plot those because there are underlying pixels. And so you can see this is probably a 1, a 1, a 1, a 6. You see they're low resolution, and so it is going to be a challenge for the algorithm to correctly classify them, although it's pretty easy to tell that this is a 3 and this is a 6. This one's a smudge. I can't tell what it is. But we can also explore the attribute variables in addition to the class variable. So what we're going to do here is just sort of at random or haphazard choose a few variables, P25, P30, P45, and P60. And we're going to look at those and their association between them by creating a grid. And so what we have here are the distributions on the diagonal for the 3 variables where 1 is in red, 3 is in green, and 6 is in blue. And then we have scatter plots, and we have really 2-dimensional density plot here. The point here is that you can see that there's separation between these things. It doesn't even really matter what the variables are, but you can see that there is separation. This is critical for our algorithms to work properly. And so now that we check that we've got the data imported, we've renamed, we've checked that there's going to be adequate separation, just a quick visual check. You can now save the data. Now I've already saved it, so I don't need to repeat this one, but the .toCSV command will take each of these data sets we've created, we'll save them as CSV so they're easy to import and get started with in the next step when we start looking at the individual algorithms. By far, the most common way to reduce dimensionality in a data set is with principal component analysis, usually just called PCA. This is a very simple and easy thing to do in Python. We'll begin by loading a few standard packages, including scikit-learn or sklearn, which gives us the PCA functionality. Then I'm going to load our data sets. We're going to load the training data, split it so we have the X attribute variables separated from the Y class variables, and then do the same thing for the testing data. And then once we've done that, we can look at the first few rows of the training data. And you see that we have 64 attribute variables, 0 through 63, P is for pixel. And then the class variable that indicates what the digit actually is here, Y at the end. We have 1, 1, 6, and so on. We'll begin by training the model with the training data. We'll set up a PCA object. That's what we're going to do right here. Then we're going to project the training data, because a PCA dimensionality reduction is like a projection, like with shadows. You're trying to find a shadow of the data that is still informative about what the original data is. Then we'll plot the variances, create a scatter plot, and get the average log likelihood for the samples. So let's do this and actually get the transformation. Now, this tells us how many dimensions are in our data. It's a rough indication. It's called a scree plot. And it tells us the amount of variance that can be attributed to each of the factors. And what you see is, even though we have 64 variables, this goes up to 64, we only need 1 or 2 to account for a large chunk of the variance in our data. That's good. That means the dimensionality reduction could be very successful. What I'm going to do then is I'm going to actually plot the projected data onto the first 2 principal components. So we're going to do just a 2-dimensional analysis. We're going from 64 to 2 dimensions, and we'll color the points by the class. That is, what number they actually represent. And what you see here is that in these 2 dimensions, it's really easy to separate the 3 numbers. The 1s are up here in red, the 3s are here in green, and the 6s are here in blue. There's a little bit of overlap, but by and large, there's a lot of separation, even though we went from 64 dimensions or individual variables down to 2 principal components. We can also get the log likelihood, which lets us know how well our PCA model reflects the original data set. And just keep that number in mind, because we're going to compare it with what we get from the testing data. Now we're going to test the model. And what we're going to do is we're going to transform the test data and get a scatter plot that uses the PCA we just calculated, the model, but applies it to the testing data. And what you see here is a very similar model. The model has transferred well from the training data to the testing data, and we still have very clear separation between the 3 different classes, the 3 different digits that are the outcome variable, even when we reduce from 64 variables down to the 2 components. And if you want to compare the average log likelihood, up here we had 185.63, here we had 180.63. The important thing is that those numbers are very close to one another, and it lets you know that the principal component analysis has transferred well from the training data to the testing data, and gives us a lot more confidence in our results as something that we can use to then move ahead in other analyses with a clearer, more consistent data set. Another interesting approach to dimensionality reduction is found in LDA, or linear discriminant analysis. What's unusual about this is it's not actually a dimensionality reduction algorithm. It's a classification algorithm that uses dimensionality reduction to do its classification tasks. So I want to show you how this works. And you'll see that to a certain extent, it looks a lot like principal component analysis, but it gives some different output. Let's start by loading several packages, including scikit-learn or sklearn here, which will give us the linear discriminant analysis function. And we'll import the dataset and split it into testing and training with X for the attribute or pixel data variables and Y for the class variable that says whether a digit is a 1, a 6, or a 9. We'll take a look at the first few rows of the training data. And here we have the first 5 rows and the variables P0 through P63, which are the number of pixels that have been activated within a certain region. And then Y, the class variable, whether it's a 1 or a 6 or something else. Now let's do the LDA model. We'll start by training it. To do this, we're going to set up an LDA object. We will fit the model to it using the training data, transform the data, plot the transformed data, and then get the mean accuracy of the classification that is based on this dimensionality reduction approach. So I'll first run this cell to set up the object, and then we'll transform the data and plot it. And what this shows us is that there is very clean separation for these 3 groups. The 1 digits are here, the 3 digits are here, the 6 digits are here. You'll notice that's bigger separation than we had when we did PCA. And that's deliberate because the way that the dimensions are created in LDA is specifically to get maximum separation between the groups. And so we're observing that it's functioning as intended. And then you can use it to actually classify the groups. So it takes these dimensions and then from those indicates whether a number is likely to be a 1, a 6, or a 9. So we'll get the accuracy here. And not surprising, given how clean that separation is, we have 99.63% accuracy on the training data. But as with any machine learning algorithm, the real test is with the testing data. So now what we're going to do is we're going to take the model that we developed and that we saved, and we're going to apply it to the testing data set. So you can see here we have LDA, which is what we got with the training data. We're applying it to the test data, and then we'll get a plot that matches the one we had above. And again, what you see here is the very clean separation. There's a tiny little bit of overlap. One of the 6s is over here. But aside from that, very similar results, great separation. And in fact, the accuracy is 99.71. It's actually a higher accuracy than we had on the training data. And so the linear discriminant analysis has used dimensionality reduction as a means to be able to separate and classify different classes of data. And it has functioned extraordinarily well in this particular situation. And is something that you could consider when you are up against a new classification situation where you have a number of dimensions that theoretically could have redundant information and could be combined through a dimensionality reduction approach. At the risk of dating myself, I have to mention that some of these algorithms I'm demonstrating simply didn't exist when I started working with data many years ago. One of the more interesting ones to me is t-SNE, or the T-distributed stochastic neighbor embedding, which is actually a method used for visualizing data that has very high dimensionality. And that means you have a lot of variables to go into it. And this is an exploratory way. Again, it's not for classification, so we don't do a training and testing split, but it's a way of visualizing the data. Let's come down and let's start by loading a few packages, including the t-SNE function from sklearn, scikit-learn. And we're going to load and prepare the data, but we're going to load all of it as opposed to the training and testing splits. We will split it into the attribute variables into X and the class variable, which indicates whether it's supposed to be a 1, a 3, or a 6, into Y. We can look at the first few rows of data. And here we have the attribute variables, which tell us how many pixels are activated within a given region. And then the class variable here, a 6, a 1, a 3, and so on. Now, in order to apply t-SNE, the one thing you have to do is specify how many components you want. And I'm actually going to put down 2 components, which makes it easy to graph in a 2-dimensional way. I'm also setting the random state to make the results repeatable. And you can get the parameters that go into the t-SNE model right here, angle and so on. You can see that we have the number of components at 2, which I just said, as well as the random state at 1. Then when it actually comes to implementing t-SNE, the one parameter we're going to be working with is called the perplexity, which has to do with how it combines the high dimensionality data down into our 2-dimensional system. Now, I'm going to start with a perplexity of 1, which you would never want to do, but I want you to see the baseline here. So here I am setting up the t-SNE. It says we want 2 components. That's what we said earlier. And here is the perplexity of 1. Then we're going to transform the attribute data. That's an important thing. And then plot the data so you can see what it looks like once the t-SNE algorithm has gone through the high dimensionality data to see how well it gets it down to 2 dimensions. Now, the thing here is you see a blob, and you also see that the 1s, the 3s, and the 6s are basically randomly scattered all over. So the perplexity of 1 doesn't do much in terms of helping us visualize things. But as it increases, you'll start to see separation of the different classes. So here I've changed the perplexity to 2, but everything else is the same. And when we do that, you see that we have separation, although the 1s are split into 2 different places. Let's increase the perplexity to 5. Now when we come down, you can see that there's clean separation between these. There is an interesting thing though. We do have this one blue point, which is a 6 mixed in with the 1s. I actually looked at the digits once, and I think this was a 6 that got written very narrow and smudged, and it actually does look like a 1. And maybe a similar thing with the 3. But we have clean separation between the groups. But let's try increasing a little bit more. Let's go to perplexity of 10. It's usually with perplexity in maybe the 10 to 20 range that is going to be most useful for t-SNE. Here we have, again, clean separation. And then let me come down and do 50, a little higher than you might want to do. But it's good for a demonstration of the boundaries of what we're dealing with. And now you see very clean separation and grouping between the classes. And so the t-SNE algorithm is simply finding a way of combining the very high dimensionality data to separate these 3 groups. And in that sense, it's a little bit like the linear discriminant analysis that we had, but it lets you know that it is possible to take this information and get it all the way down to these 2 dimensions in terms of separating the groups. And that's an example of effective dimension reduction. Now that we've gone through several algorithms for dimensionality reduction, I want you to have a chance to do a little hands-on work with this, doing a challenge in PCA, or Principal Component Analysis. For this, I'm going to ask you to set up a PCA object, project the data onto those dimensions, plot the ratio of variances, and then get a scatter plot of the projected data along the first 2 principal directions. This mirrors what we did in the PCA demonstration. Now, to do this, I'm going to introduce you to a data set that's called Swiss. This is a well-known data set. It comes from census data of a sort from 1888 in Switzerland. It gives standardized fertility measure and socioeconomic indicators for 47 French-speaking provinces in Switzerland, again in 1888. And we're going to use this complete data set as opposed to separating it into training and testing. I've saved it as a CSV file in our data folder, so let's start by importing it. And then I want to show you just the first few rows. So what we have are just a few dimensions here. We have a fertility rate, which is expressed as a percentage. Agriculture means how many people are working in agriculture. Examination scores, education levels, percent of the population that's Catholic, and infant mortality rates. And what we're going to do is we're going to combine those dimensions, if we can, using PCA. Take a minute, see how you can get it, and then we'll come back and compare solutions. And now I'd like to compare solutions to the PCA challenge. What I'm doing is I'm following the template we had in the PCA demonstration, but I'm going to come down and start by importing the libraries and then importing our data set, which again, we're not splitting it into training and testing. We're going to do it all at once. It's the Swiss data set. And here's the head, the first 5 rows that we saw previously. To actually do the principal components analysis, it's really straightforward. Again, using the template we had before. I set up the PCA object, transform the data because they're on different scales and you need them to be on similar scales. This standardizes them to do that. And then plot the variance explained by each component. And what you see from this is you have a maximum number of components that matches how many variables or features you had. And you can see that the first one explains a lot. Well, then we go down a little bit, and by the time you reach the end, you're not adding anything interesting. So we really have about a 2-factor or 2-component solution. This has 0 index numbering. So this is the first one and the second one. Now let's plot it. And what we can see here, because we do not have a class variable separating these things, but you can see that there is clean separation. On the first dimension here across the bottom, we have a group over here, a group over here, and a big space in between. I happen to know the data set well enough to know that this is going to be separating the Catholic and non-Catholic areas in Switzerland in 1888. And then we have a secondary dimension in which they're both spread out. And so we can go from the original 5 dimensions down to these 2, possibly even 1, as a great way of reducing the data and helping direct further questions and insights that we may be able to get from the data. Libraries are the original big data, and a great place to go mine data for insights. But the value of a library is only partly in the books that it holds. What makes the library useful is that the books are organized in a meaningful way. But as you might guess, there are many different ways to organize books or to put them into meaningful clusters. For example, there is the Library of Congress classification system, where QA 276 is where I often end up looking for statistics books. Or there's the Dewey Decimal System. The same books might be under 006. There's the Harvard Yenching classification. This is English classification system for Chinese language materials. I know other people who've classified books by size or by color. You can do ISBNs, the name of the author, the publisher, and so on. The point is, there are a lot of different ways of bringing order, but the thing that matters is that you bring order. And you do that by putting like with like, putting similar things together. The goal of any system is to put these together like sorting flowers at the market so you can find what you're looking for and find similar things next to it. But as you might guess, there are a few important things to keep in mind about how you cluster things and the systems that you use. Number one is that with clustering, there is no correct answer. This is not do you match with the correct classification. There's no correct way to categorize your music. You can do it by genre. You can do it by how often you listen to it. You can do it by the time of year you listen to it. Any of those work. There's no correct system. That's different from classification. Also, any clustering system is going to be based on the data that you actually provide to it. If you only provide a little bit of data, the clustering is going to be limited in its effectiveness. And then also, clustering is designed to serve practical goals. Again, there's not a single correct answer, but it's something like if you have enough marketing budget to do 2 marketing campaigns, then well, try to get 2 clusters, and then those will allow you to tailor your campaigns towards those 2 groups of people who have at least something in common with each other. All of these systems rely on some concept of similarity between the cases or observations. Typically, the data is represented as though it were in a multi-dimensional space, X, Y, Z, and so on, where you have one dimension for each variable in your data set. If you have 100 variables, you have 100 dimensions. If you have 1,000 variables, you have 1,000 dimensions. Now, when you're looking at these dimensions, one thing that's very handy is to standardize the dimensions. Because say, for instance, you're measuring people's height in feet, and they are 6 feet, and you're measuring their weight in pounds, and they're 180 pounds. Those are very different numbers, and larger numbers tend to dominate. And so you want to standardize them, usually so each variable has a mean of 0 and each variable has a variance or standard deviation of 1. That gives them the potential for equal influence. Then what you do is in this multidimensional space, you measure the distance between 2 points. And there are different ways of measuring that distance, but they all come down to how close are these. And then one thing you do is you look for dense areas. Are there places in this multidimensional space where a lot of points are clumping? That would be a cluster. Now, I want to cover 3 common ways of doing clustering in this course. The first one, and the one I probably use the most often, is hierarchical clustering. This is where you take all the cases and then you arrange them in a hierarchy. Now you might have an agglomerative method. This is where all the cases start separately. They're each in their own little category. And then the 2 cases that are most similar get joined into a group that now just has 2. Then you look for the 2 cases after that that are most similar, and you go on until all the cases are joined. The flip side of this is a divisive method. All cases start in one super category, and they are gradually split off one case at a time in the network. And then a graph like the one you see here is a dendrogram. This shows all the individual levels of splits, and it allows you to focus on the levels that are most useful for your particular purposes. Another very common method for clustering is called k-means, where k is a number. It's how many groups you want. So if you want 2 groups, k is equal to 2. If you want 10 groups, k is equal to 10. And what your algorithm is going to do is find k centroids in a multidimensional space. A centroid is like a mean, but in several dimensions. And you can think of it as each of these balls as representing a center in space. And then what the algorithm does is it assigns cases to the closest centroid, and then it may recalculate the centroids as it goes through. Now, as you might guess, this system works really well when your data falls into these nice balls. It works best for spherical, non-overlapping clusters, but that may very well be the case. In that situation, you can get very clean separation, and you can specify, again, how many clusters you want. You want 2, you want 5, you want 10. It's up to you. Another method I want to demonstrate, even though it's less common, is called DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise. And I picked this picture because I like to think of it as banana scan. And the reason for that is it works on local density. If you're trying to find a point in space and assign it to one of these bananas, well, DBSCAN is going to work well because it works with non-convex and non-linearly separable clusters. DBSCAN can tell that a point in a banana at the end belongs to that whole elongated, curvy banana and not to the other banana that's closest to it. Also, it can get points that are classified as noise, like these individual banana slices. They're no longer part of one of the bananas. And so the algorithm will know to ignore those and not cluster them with anything else. And so we're going to look at 3 methods. We're going to look at hierarchical clustering and k-means, both of which are exceptionally common. And then we'll look at DBSCAN as an interesting alternative. There are, of course, other methods, but these 3 are going to get you a very long way in terms of finding useful and hopefully actionable clusters in your data. For our demonstrations of clustering, we're going to use a data set about penguins, the flightless waterfowl from the Antarctic and Southern Hemisphere. To access this data set, you're going to need to install a library called Palmer Penguins. You might be able to use this shorter command, uncomment it and run the cell. Or in my case, I use the longer, more explicit command, but it only needs to be done once per machine. And once you've had that installed, then you can go ahead and load the following libraries, including this one that lets us load the penguins data set. Now, we're going to do a few things here. We're going to load the data set. We're going to remove some of the variables that are not helpful for what we're going to do, rename the class variable, drop the rows that are NaN or not a number, missing data, and then we'll take a look at the first 5 rows. And that's what all of this is going to do. Load it, drop variables, drop missing data, rename columns. So the class variable, the species is Y, just makes things easier, and take a look at the first few rows. And so what we have are 5 penguins here. These are all Adelaide penguins, and it's giving them the length of their bill, the depth of their bill, the length of their flipper, and their body mass in millimeters and in grams. And from that, we're going to see how well we can cluster these 3 different species of penguins. It's helpful, however, to explore the data a little bit more. Let's see how many of each species of penguin we have just by making a bar plot. So what you see is we have a little more Adelaide penguins than we have Gentoo or chinstrap, only half as many as Adelaide. But we still have a good number of each of them. And then it's also nice to look at the relationship between what might be the predictor variables. And so to do that, we're going to use Seaborn's pair grid, and we'll look at the bill length, the bill depth, the flipper length, and the body mass. And it takes a moment to do this. But what you can see here is the Adelaide are in red, the Gentoo are in green, and the chinstrap are in blue. And there's nice clean separation. These are histograms down the diagonal, with scatter plots on the lower half and density plots on the upper half. And it's clear that we're going to be able to separate these species pretty well. And then finally, you can save the data, although I've already done it. I've saved it as a CSV file in our local data file, and you might be able to access that more easily in the future. But with that, let's get started on looking at methods for clustering in Python. One of the most useful methods for cluster analysis is an exploratory method called a hierarchical clustering. What makes it exploratory is it actually shows you every possible level of clustering in your data. It's a very common approach, and it has a great visual output. So let's start by loading a number of packages, including sklearn and scipy for clustering and visualization. I'm going to load the penguins dataset from the CSV file that I saved previously, and I'm actually going to reduce the number of cases because the graph that we're going to make actually labels every individual case. And if you have a lot, you just can't read it. We're going to also separate the class variable, drop it from the original dataset, and take a look at the remaining data. So what we have here are the measurements of bill length, bill depth, flipper length, and body mass for 5 penguins. We have saved separately what species they are. But let's come down here to hierarchical clustering. We're going to use a function from SciPy to do this. Scikit learn can do it also. There are 2 important functions, linkage and dendrogram. Linkage does what's called agglomerative functioning, which is where you start with all of the cases separate, and then it starts to combine them as it goes up the hierarchy until you end up with one overall supercategory. Various linkage methods or ways for deciding how close 2 cases are can be used. We're going to use word linkage, a common method. You can also do average, single, or complete. But let's come down here and let's use linkage, apply it to DF using method, word, and then a Euclidean measurement metric. We'll save that to HC for hierarchical clustering, and we'll make a graph that's called a dendrogram, which means branches. And so when we do that, it's going to be a really tall graph, and the tall part, you would think that you want to shrink down the dimensions, but we need to have enough height so that we can get things down here at the bottom. What you see here are 75 labels, because we reduced the data set to 75, for chinstrap, Adelaide, and Gen 2 penguins. And these graphs indicate how they get combined. And what you see here is that the Adelaide and the chinstrap tend to get combined with each other. They're in this one overall category, but within each of these subcategories, they seem to cross over a lot. On the other hand, the Gen 2 seem to be relatively different from the others, although there is some crossover. And so this gives us a clue as to how other clustering mechanisms might work and the overall similarity and differences between the species. And that's going to help us when we try to interpret the results of our other methods, k-means and DBSCAN. Sometimes you know how many groups there are, and sometimes you know that those are the clusters that you want to use. In that case, instead of doing hierarchical clustering, which shows you every possible level of clustering, you use k-means, which allows you to specify how many groups there should be, where the number of groups is k. And this is a very common method as well. You can think of it as something, for instance, that's also used in marketing research, where you know how many campaigns you can run, and you need to find groups that fall into each of those. So k-means is a very useful, frequently used approach, and let me show you how to do this in Python. We're going to start by loading a number of libraries and several functions here you see from Scikit learn. Let's load those. And then I'm going to read the data from the CSV file, split out the class variable into Y, standardize the other variables because they're on different scales and need to be on the same scale, and take a look at the first few rows. All right, and we've seen this one before, but now we see it with standardized scores that have, for the entire group, they'll have a mean of 0 and a standard deviation or variance of 1. Now we're going to run k-means, and we're going to do this a couple of different ways. We're going to start by setting up the k-means where you have to tell it how many clusters you want. You can set a random state to make your results reproducible. The initialize, where you tell it how to get started, we're going to simply use k-means plus plus, a common method, and then how many iterations it should go through. Now let's come down here and let me show you the important one. I'm telling it that we want 3 clusters because we know there are 3 different species of penguins. And the rest of it, we can just run all of that. And this gives us the parameters it used. But let's visualize the clusters and see what they actually look like. To do that, we'll create a scatter plot and we'll add cluster centers on top of the scatter plot that we're going to number. And so here's our output. What we have are the Adelaide penguins over here, the Gen 2 penguins over here in green, and the chinstrap here in blue. And we're looking at just 2 dimensions right now. We're looking at the bill length and the bill depth. But in addition to that, you can see that we have 3 red X's, one right here, one right here, and one right here. Those correspond to the 0, 1, and 2 over here. Those are the centroids, or the multi-dimensional means or centers of each of the 3 groups that the k-means algorithm found. Now, they happen to correspond closely to the 3 different species, but in situations they could be different because it's simply looking for the similarity between individual cases. Which brings up another question. What if you don't know what value of k you should use? Well, I want to show you another method. We're actually going to go through an algorithm to find what appears to be the ideal number of groups, k. That's the grid search CV object. And then we're going to use a silhouette score. Remember, this is kind of like dimensionality reduction, and you're looking at shadows here. And let's come down and create a custom scorer, list the values for the parameters. I'm starting at 2, so it could go anywhere from 2 groups or 2 clusters up to 10 clusters. And then we set up the grid search CV object, and we'll display the optimum model. And when we do that, look what it told us. It actually says that the ideal number of clusters based on the data that we gave it is 2, not the 3 species, but 2 different clusters of penguins. And so let's plot those parameters. And what you can see here in terms of the silhouette score, this is the total number of centers or groups. 2 has the highest. 3, which is what we would expect because there's 3 species of penguins, is lower. And then it drops down dramatically after that. So we're actually going to try doing this with 2 as an empirically driven solution to the clustering question. So let's visualize the model that it gave us, where we tell it the number of groups that we want is going to be driven by the parameter that it found earlier. So I'm going to run this one right now. And the scatter plot with the measurements on the bill length and the bill depth for the penguins looks exactly the same as what we had before. That hasn't changed. What has changed is where the cluster centers are. Remember, these are multidimensional. There's actually 5 dimensions here. Multidimensional centroids for each of the clusters that it found. And so they're slightly moved over. Here's the first one. It's between the Adelaide in gold and the chinstrap in blue. And then the Gen 2, which we saw earlier in our hierarchical clustering, is kind of different from the others. Their centroid is still kind of in the middle of their species. This gives us an important insight into how clustering works. Clustering is based on the exact cases or observations you gave them and the exact variables or data you gave them. We only had 5 measurements that we were including on a specific set of penguins. It's possible if we had a larger set of variables, or if we had more observations, that the centroids would turn out differently. But for right now, we empirically have a suggestion of 2 clusters in our 3 species of penguins. The final method of clustering that I want to show you is called DBSCAN, for density-based spatial clustering of applications with noise. It's a very long name. But what DBSCAN is really good for is when you don't have nice, tight, little spherical or at least convex groups. When you have groups, for instance, that are in circles or rings, or they have irregular shapes. DBSCAN does this by building up from individual neighbors and really doing an accretion to get a cluster. It also can leave certain points out, saying this one appears to be noise. Let's see how this works with the penguins dataset. We do this by loading a number of libraries and functions, including DBSCAN from the Scikit Learning Library. I'm going to read the dataset from the local CSV file, and as before, I'm going to read the data from the local CSV file, separate the class variable into Y, standardize the other measurements, and display the first 5 rows. And what you see here are we have 4 measurements: bill length, bill depth, flipper length, and body mass, now standardized so that they have a mean of 0 and a standard deviation of 1. But now let's come down to the DBSCAN clustering algorithm. There are 2 steps here. Number one, we need to determine what our parameters should be. There are two things in particular we need to look at. The min samples, or minimum number of neighboring points for clustering. So when you're assembling a cluster, how many points do you want to have as you are putting together that cluster? The second one is epsilon. That's the neighborhood radius. Think of it as like a physical measurement, how far out you're going. And to do this, to find the value we want for epsilon, we need to look at distances of min samples and look for a bend in a graph, like a knee. And what you see here, this is our graph and it bends right here. And that looks like a value of 0.6 will be about the best one that we need for our data. So now we can take that value and fit the model. See here, we're going to call DBSCAN and we're saying use the epsilon value of 0.6 that we got from our graph above. The min samples is K. We specified that already, and we can graph it. And this is a graph that I'm going to have to zoom in a little bit. So here's what's happening on this one. It's showing us the two dimensions, the bill length and bill depth that we've used before, even though there are 4 physical dimensions that it can pick from. And then we have the Adelie penguins in gold. We have the Gen 2 penguins in green and the chinstrap in blue. But the shape of the marker is important. What we now have is that DBSCAN found 4 groups. This is interesting because we know that there are 3 species, although one of the methods we used with k-means suggested there were 2 clusters, but DBSCAN found 4 clusters. And the reason this is different, again, is because it can do different unusual shapes. It's not looking strictly for a sphere. It can look for something in the 4-dimensional space that's a little different. And so what we have is a cluster marked with circles. Those are mostly Adelie. We have a cluster marked with X's. Those are also mostly Adelie. Although we have circles here over the chinstrap, and then we have pluses to indicate one of the groups. Those are mostly chinstrap. And then down here, the Gen 2 are almost entirely marked with squares, except there's a couple marked with circles that indicate they're probably a little more similar to the Adelie and the Gen 2. And so this again is a different way of getting some insight into the clusters using a method that allows us to adapt to some of the peculiarities of real data. That's the value of DBSCAN, and it can be something that can be of tremendous use in the applied work that you do with cluster analysis. And now it's time for you to get a little practice doing these methods with a new data set. For this, I'm going to invite you to do k-means on a very well-known clustering data set, the iris data set, as in iris flowers. I'm going to invite you to import and prepare the iris data set to conduct a k-means cluster analysis with a value of 3, and then visualize the clusters. To do that, we'll import these libraries. And then I've saved the iris data set as a local CSV file in our data folder. Let's take a look at the first few rows. What we have, by the way, are 150 observations of 3 different species of iris flowers. And we have the species located here in the last column. And we have 4 physical measurements, the sepal length and width, and the petal length and width. And from that, you can see how well you can predict the 3 different species. Give that a try. Do the k-means algorithm, and then we'll meet back here to compare answers. Now that you've had a moment, let's see how we can use k-means with the new data set, the iris data set. As before, I'm going to load a number of packages, and I'm following the template that we had when we did k-means on the penguins data set. Then we'll load the data set from the local CSV file and take a look. We have 4 physical measurements on different scales, and we have a species variable. Well, I'm going to rename species as Y, remove it from the original, save it on its own, standardize the other variables, and take a look again at the first few rows. And now what we see are z-scores. These are all done so that they have a mean of 0 and a standard deviation of 1. And we've saved the class variable, which gives us the species, in a separate object, lowercase y. Now let's do k-means, and we use the same code that we had before. That's one of the advantages of standardized names for objects. We're telling it that we want 3 because we know that there are 3 species of iris. I mentioned that in the challenge. And otherwise, we can simply use the code that we had with the penguins dataset. This describes how it's going to work, but now let's visualize the clusters and see how well it performs. And what we get here are the setosa irises over here by themselves. And you can see that one of the K or 3 centroids is right here in the middle of it. There are 2 other physical measurements, but this appears to be a well-defined group. Then we have the versicolor in green and the virginica irises in blue. And you can see there's a fair amount of overlap between them. If we looked at the individual distributions, that would be obvious as well. And so we have 2 clusters, one here and one here, that both include both species. So we do have 3 different groups, but they don't correspond absolutely to the 3 different species. But nevertheless, if you were doing something with a very practical focus, again, like segmenting an audience for campaigns, you don't necessarily care that people come from 3 different states. You want to know what 3 different groups of people are most similar to each other so you can give them the same campaign. That's functionally what we have here. We have 3 species and we have 3 clusters, but there's a slightly different association of each flower between the species and the cluster. And for a practical approach, this can be exactly the thing that you're looking for. We've talked about clustering, which is putting similar things in similar piles, but sometimes similar is not enough. For example, when it comes to the mail, you can group things by size or shape or postage, but that's not what you're going for. Your one job is to put things into the right box. So if you want to think about clustering versus classifying, which are probably the 2 most important things happening in data science, clustering is just trying to find similarities, and the data is referred to as unlabeled because it doesn't have a correct category that you're trying to match. That also means that the answers are subjective. What that really means is you could do things in different ways, and the usefulness or the utility is the outcome by which things are judged. It's also an example of what's called unsupervised learning. Unsupervised means, again, there's not a correct category here. It's just trying to find things that are relatively similar to each other. Contrast that with classification. This is where you have existing categories, like this is this person's mailbox, or this is a photo of a toy. This is a photo of a tree. You want to place new objects into existing categories. And so the data here is labeled, which means there actually is a correct answer. And in many cases, it's there in the data. Also, the answers are more or less objective because there is a correct answer. Does this mail go in this mailbox or does it go in that one? And in that case, you can judge the effectiveness of the algorithm by how accurate it is. Were the positive cases labeled as positive? Were the negative cases classified as negative? And it's also generally referred to as supervised learning because you have this label, this correct category that is used to teach the algorithm how to process the data to get to that final outcome. Now, there are several methods that are used for classification. In fact, there's an enormous number, but I want to show you a few that are really common. The first one is called KNN, which stands for K nearest neighbors, where K is a number that you choose. It could be 3, it could be 5, it could be 11. And the idea here is that existing categorized cases are located in a multi-dimensional space. If you have 10 variables, then you have 10 dimensions, and each dot in that 10-dimensional space is where a known observation goes. And then what you're trying to do is you're trying to locate a new case in that 10-dimensional space and then compare it to the K closest points in that physical space. Those are its nearest neighbors. You generally choose an odd number, and again, maybe from 3 to 9 to 21, something, and you simply assign that new case to the same category, to the most common category as its K nearest neighbors. It's like deciding with berries. If you find a berry in the wild, these are all berries. Would you eat them? Now, some of these I know what they are. I know blueberries, I know raspberries, I know blackberries, but two of those are not very familiar to me, and I would probably stay away from them because I do not have a ready categorization system for deciding whether they're safe or not. Another approach that's often used in classification tasks is called naive Bayes. This uses a formula developed by the Reverend Thomas Bayes, that's why it's called Bayes, to calculate probabilities. And the major breakthrough that Bayes had was a method that combines base rates, how common something is overall, and prior probabilities to get posterior probabilities. So it's often used as an example in diseases. How common is a disease overall? That's its base rate. And if a person has a disease, what's the probability of getting a positive test result? That's a prior probability. The posterior probability is if somebody gets a positive test result, what's the probability they have the disease? And that's usually the one that most people are interested in. And so it's used in a lot of situations, including classification. And it's called naive, not because it's simplistic, but because it assumes that each of the predictors operates independently. It's like rolling these dice over here. You roll them. What happens on one does not affect what happens on the others, but you can calculate the probabilities between them. And the last method I want to show to you is decision trees. And this is a series of yes-no decisions, binary decisions. And the algorithm chooses the most informative split at each point. Think, for instance, if you're playing the game Hangman where you're guessing a word, you choose letters that are diagnostic. E is going to be the most common. A, those will give you an idea what's probably going to be in the word. On the other hand, if you first guess X and it says no, you haven't eliminated very much. That wasn't an informative choice. So the algorithm goes through the data, chooses the most informative split at each point. The neat thing about it is it works with basically any kind of data and almost any kind of pattern. It can use quantitative data. It can use categorical data. It can use binary, multiple categories. It can use skewed data. It can work with almost anything, often in its raw condition. Also, because you have this graphical output, decision trees are exceptionally easy to interpret. And so there are many, many more choices. You don't have just one pencil, one color. You've got a lot. This is because classification is one of the most important tasks in data science and an area of very active research and development. And in data mining, you do have a choice of dozens or possibly hundreds of methods. But the three that I mentioned are the ones that I want to demonstrate that I think will be probably of greatest use to you as soon as possible. To demonstrate several methods for classification in Python, we're going to be using a dataset called SpamBase, which contains information about spam emails and not spam emails, and describes each email according to a range of things like, for instance, do they use all caps, exclamation points, and do they use this particular word, yes or no? Things that can be used to diagnose whether something is spam or not. To do this, we're going to first import some common packages, including scikit-learn, that will be able to do the test train split. And then we're going to import a dataset. This dataset comes from the machine learning repository at the University of California, Irvine. And you can access it directly at this URL if you want more information on it. But I've saved a local CSV to make life easier. And you can run this command to import that CSV file. Let's take a quick look at what we've imported. What you see are 5 rows numbered 0 through 4 and a whole bunch of variables numbered 0 through 57. Each of these are different attributes that measure various things about spam email. They're on different scales. It's this last one that's really important. That is whether it is spam or not. So what we're going to do is prepare the data by renaming the variables as x0 through x56, and then put the last one as y, which is what I always use for the class variable. And we'll take a look at the data again. Now we have x0 to x56, and then y, the outcome variable, which is either 0 or 1, 0 for not spam, 1 for yes, it is spam. Classification is usually done with machine learning algorithms that benefit from a train test split. And that's what we're going to do right here. We're going to split the data so that 30% goes in the test, 70% goes into train. And then we'll be able to do our modeling on the training and then test it, of course, on the testing data. So let me run this right now. And let's explore the training data a little bit. First off, let's get a bar plot of our class variables to say how common the two categories are. 0 is not spam, and we have almost 2,000. 1 is spam, and that's about 1,250. So they're not identical numbers, but they're not grossly out of balance. So that helps. Now let's take a look at the attribute variables, the things that are used to predict spam. We're going to do one simple thing here. I've chosen rather arbitrarily for the different variables. I don't even know which ones they are. And we're going to graph those and then color things by whether they're spam or not. And when we scroll down, we now have different colors. The non-spam messages are red. Here we have it. And then the green ones are spam. The important thing here is they have different distributions. And you can tell we have outliers on these, which explain the curious empty areas because there is data out there. But it looks like we have separation on these, probably enough separation to do something useful. And that's the amount of preparation that we need to do. Now you can save them as the DF, the complete data frame, the training TRN or test TST. I've already saved them in our data folder. So we're good to go to start looking at the algorithms for classification in Python. In the natural world, it's often the case that like goes with like, and the K nearest neighbors algorithm, or KNN, is an example of that, where the K is the number of neighbors you want to look at. The idea here is that you put your data in a multidimensional space, and if you're trying to find out if a new case should go into one category or another, you look at its closest neighbors in that multidimensional space and see what's most common among them. Theoretically, it's a pretty simple thing. To do this in Python, we're going to start by loading a number of packages, including several functions from scikit-learn. Once we get those, we can load the data. We're going to load the training data from this local CSV file, and then we'll split it up, and then we'll do the same thing with the testing data, and then we'll define the class labels. Let's take a look at the first few rows of the training data. Again, we have x0 through x56 as the different variables or elements of the emails that are being measured in one way or another. And then here at y is whether that email is spam, that's a 1, or not spam, that's a 0. Let's come down and train the model for KNN using the K neighbors classifier. To do this, we just run this one command. That's pretty quick. And we can actually get the mean accuracy on the training data. And it's not really high. It's about 87% accurate. On the other hand, spam emails are kind of wiggly. They adapt very quickly. And maybe 87% represents a pretty good accomplishment based on the data that we have given the algorithm. Now let's go down and optimize the KNN model. We're going to actually try to find out what's the best number of neighbors to look at. How many nearby data points should be included when trying to classify a new observation. So what we're going to do is we're going to set up this classifier object. We're going to give it the range of parameters. We're going to say at least 3, no more than 15, and move up in 2s. That's the important part, and we'll get the optimum model displayed below. We'll plot that with this command right here. And what you see here is the number of neighbors going from 3 up to 13 here. And this is the mean cross-validation score. It's accuracy. And you can see this red dotted line shows that we're highest at 3. So that's the number we're going to use as we develop the model. Now let's come down here to the test model and get what's called a confusion matrix. And what this is we're going to take the KNN model we've developed. We are going to automatically tell it to use the 3 neighbors, the best solution that we got above, and then tell us how many cases got accurately categorized using the model from the training data, but applying it to the test data. And we get a little multicolor box here. What we have on the side is the true label. So these are emails that are genuinely not spam across the top. And these are emails that genuinely are spam. And then from that, we have whether they are predicted to be spam on the right and predicted not to be spam on the left. And so ideally, you want to have all of your observations in this cell and in this cell, because that would mean true positives and true negatives. But it turns out we have a small number of false positives. 15% of the non-spam messages were identified as spam. And this right here, the 26%, is the false negative spam messages that got through the filter. But this is a great way of getting the general performance of the algorithm applied to this particular data set. We can also get the mean accuracy on the testing data, where it's 81.17%. So it's a little lower than what we had with the testing data. But again, we don't have a huge number of variables here, and we're using a basic, well understood, and really sort of easy to conceptually visualize algorithm, the k-nearest neighbors. We'll compare that to the performance we get with other algorithms, but this is a great starting point for any classification task. A compelling choice for classification in the data mining context is the naive Bayes model. And as I explained previously, Bayesian models are used to take observed probabilities and prior probabilities, and from those calculate posterior, or you might say observed probabilities. How likely is something based on the data that we have and what we knew beforehand? The naive part means that the individual variables are treated separately, which dramatically simplifies the calculations going into it, and it turns out to function effectively in a wide variety of situations. We'll do this by first importing a number of libraries, including some from scikit-learn, which will give us the functionality for naive Bayes. Then we'll load and prepare the data from the local CSV and split it into the training and testing parts. I'll take a look at the first few rows. We've seen this before. These are the attribute variables of the emails, and this over here, Y, indicates whether it's spam or not. Now we can train the model, and this is really simple, easy code. All we have to do is say we're going to use the Gaussian meaning like normal distribution, NB for naive Bayes, and that we're going to fit it to xtrain with ytrain as our class variable. So quick and easy and very fast on our information. And from there, we can calculate the accuracy applied to this data set. And on our training data, we have 82% accuracy, which is about what we had with our other approach, k-nearest neighbors. We've actually done creating our model here, and we can apply it to the testing data set now. And we'll do this by coming down and creating a confusion matrix to see the number of true and false positives, true and false negatives. And what you'll see, this is not spam, 74% and 26%. And then these are true spam messages. And then on the right are the ones that were predicted to be spam. And these are the ones that were predicted not to be spam. So again, if everything were working perfectly, all the cases would be here as true negatives or here as true positives. We do, however, have a small number of false positives. That's the regular messages that were identified as spam. That's 26% of them. But we have a much, much smaller number of false negatives. Those are spam messages that were identified as not spam, and that's just 6%. We can get the mean accuracy here. We see it's about 82%. But because things are a little unbalanced, you may want to try juggling around some of the parameters in the naive Bayes model to see if you can get more balanced performance in terms of false positives and false negatives, again, according to what's most important to you. But that's another method, naive Bayes, very easy to execute in Python with scikit-learn, and very easy to check the results on that. I'm a visual person, and consequently, one of my favorite methods for classification is decision trees, because it gives you this graphical output that can be so easy to interpret and get insight into what's happening in the classification process. To show you how this works, we'll start by loading a few packages, again, going back to scikit-learn, and then loading the spam-based data, which we will again split into training and testing. And we'll again look at the first few rows. These are the attribute variables, x0 through x56. And here's the class variable, y at the end. And we'll do a decision tree now. We'll use the decision tree classifier object from scikit-learn. Really easy to do. All we need to do is tell it what our criteria are and the number of leaf nodes. And we can then fit it to the training data. It's a very quick model there. And from that, we can actually get the mean accuracy. And it's 89%, almost 90, which actually is, you may recall, higher than what we had with our other algorithms. Now what we can do is we can optimize the decision tree by going through a few different parameters. We can get a range of values for the max leaf nodes and 2 possible values of criterion. This lets us try a few things, and we'll use 5-fold cross-validation on this process. And when we do that, we first get a list of the parameters used in this search, but let's take a look at the plot that it makes for us. There are 2 things that we're looking at here. Number 1 is the entropy, and the other one is the Gini index. And we can look at those as a function of max leaves. And the red dotted line here shows us where this is the highest. And it says that the Gini model here with about 38 leaves is going to be the best approach. So we can then come down and display the decision tree by plotting that. And what you see is each criterion, if the variable x52 is less than 0.054, go this way, go that way. And it's easy to see how it's going through the process. It goes a little further than this, but you get the beginnings. You can print out the entire model if you want to. But I want to go ahead and test the model by taking this tree and applying it to the testing data. And here's our confusion matrix, which we've seen before. These are the true spam messages on the bottom, and these are the true not spam messages on the top. And what you can tell is that we've got better accuracy. Again, you want everything to be true negatives here and true positives here. We have very few false positives, and we have a relatively small number of false negatives. So that's good. And we can get our mean accuracy right here, 91%, which is extraordinary given the other models we compared where we're about 81%. And so the decision trees, both having a visual method, would make it easy to see the process by which it's classifying things. And we're getting a higher accuracy in this particular setting, which suggests that this is always something that you would want to consider when you're confronting a new classification task. Keeping spam emails out of your inbox is helpful, and I'm grateful for it. But when it comes to data mining and machine learning, some tasks are life and death. And in this challenge, I want to invite you to apply one of these approaches, the KNN, K-nearest neighbors algorithm, to a data set about breast cancer. To do this, I'd like you to import and prepare the breast cancer training and testing data sets, prepare the data, train and optimize the model, plot the accuracy of the parameters, apply the KNN model to the training data, graph the confusion matrix, and get the overall accuracy of the model on the testing data. This is following the example we had in the KNN presentation. Now, I want to show you a little bit about the data set. So I'm going to start by importing some libraries. Then I'm going to import the data. This is another data set from the University of California, Irvine Machine Learning Repository. You can get to the original data set with this link, but I've prepared the data set a little bit to make it easier to manage and saved it as a local CSV file. In fact, as 2 local CSV files, one with the training data and one with the testing data. I've removed the ID variable. I've renamed the variables x0 to x8. I've renamed the class variable, which indicates whether a tumor is benign or malignant, to y, converted all attribute variables from unordered categorical to numeric variables, dropped cases with missing values, and then split it into the training and testing sets. So let's open those 2 by importing them and take a look at the first few rows of the training data. And so what you have here are 5 rows, and these are observations for cells that are being biopsied, and then the determination whether they are benign or malignant. And the question is that whether these measurements can be used to determine whether a cell is cancerous. Take a minute, see what you can do with KNN, and then we'll come back and compare answers. I'll see you in a moment. Now that you've taken a moment to try the KNN challenge, I want to show you the solution that I have, which is based on the original demonstration of k-nearest neighbors. I'm going to start by importing the libraries, including several from Scikit-learn, and then loading the data that we prepared. And to do this, I'm going to import the data and then split it into the attribute variables, which are used for predicting what's going on, and then the class variable, which is the outcome we're trying to predict. And then I'll finish with the class labels that say whether the cell is benign or malignant. Take a look at the first few rows of the training data. And we have X0 through X8, which are measurements of the cells in the biopsy, and then Y, the class, the determination whether it's benign or malignant. We'll train the model, which is a very simple procedure once you have the k-neighbors classifier, and I'm just putting in 5 neighbors here. We'll run that one, and then we'll get the mean accuracy. And it's 98% accurate. That lets you know that based on these measurements, it's pretty easy to distinguish benign from malignant cells. But we can also try optimizing the KNN model. We can do this by finding the ideal number of neighbors. And what I'm going to do right here is this one is the search, where we're going to look for a number of neighbors from 3 to 15 going up by 2. And what we get here is it's telling us that 13 was the ideal solution, but we can plot that to make it a little easier to see. And what we have here is a graph that looks pretty dramatic, but please note these are very small differences in performance. We're going up 0.1% with each of these, but it does show that 3 to 9 was equivalent. And then we had a jump when we get to 13. That's why our red line is there. So we can take that and we can apply that here when we test the model. We're going to get a confusion matrix, and we're going to tell it to use the best KNN model, so 13 neighbors and the other parameters, and then use the X test variables to predict the Y test class outcome. And let's run that one, and we get a confusion matrix. And now what you see is the way you usually want these to be. We have a very high percentage of true negatives. So these are cells that were predicted to be benign, and they are in fact benign. And then 94 for the malignant cells that were predicted to be malignant. We have only 3% false positives, and we have only 6% false negatives. So based on the information we have, it appears to be a highly accurate model. In fact, we can come down and get the overall accuracy on the testing data right here, 96% overall based on these measurements that we had. Again, sometimes you can use these classification models for saying what's in a picture or whether something is junk mail or not, but sometimes you get to do something truly meaningful in a life and death situation, and this is one of those great examples. Association analysis, also known as association rules mining, is actually better known as market basket analysis because it's used to figure out the things that people are going to buy when they're shopping in the market. The idea is you're trying to find some sort of if this, then that logic to build up rules. If a person buys an orange, what's the probability they'll buy a grapefruit? If they get both of those, what's the probability they'll get a lime or a lemon? And the ability to specify those rules, those associations, allows you, for instance, to place things near each other in the store, or to offer an incentive. If you bought this, we'll give you a discount on this one over here. And so association analysis or association rules mining can be extraordinarily useful within commercial settings, but within many other situations. And I'll give you a few examples of those. Now, most of the time when we think about working with data, we think about data in a tabular format with rows and columns. And so here, for instance, you might have customers listed in one. You see, we've got our 4 customers with Ava coming again at the bottom. We have the date of the transaction, and maybe you have one column for each item that they could purchase: apples, bananas, cherries, and dates. You put a 1 if they purchased it in that transaction, and you don't put anything if they didn't. That gives you kind of a sparse data set, or you could fill it in with zeros. But this is the rows and columns that most of the time when we work with data, this is what we're used to. And association analysis can work with this kind of data, but more often the data is provided in a transactional data format. So we have the customer here on the left, we have the date of the transaction, and then we have this single entry that is items with all the things that they bought, maybe just separated with a comma. And sometimes it's going to be a really long list. This is a very different kind of data. And while you can split it into the columns, most of the algorithms that we're going to be using work really well with this transactional data format. I want to show you two really common methods for doing this kind of analysis and one less common application of it. By far, the most common is an algorithm known as Apriori. And it's the most common method, and it really just involves counting things, counting individual items and item sets or collections of items. You can do some of this on your fingers. 1 here, 2 here. It's pretty straightforward. You then create conditional probabilities. If they bought this, what's the probability that they bought that? The nice thing about it is it's super easy to interpret the results. A very closely related algorithm is called Eclat, which is actually a portmanteau for equivalence class transformation, although Eclat is also the French word that refers to the gleam or the glare of the sun. So I've got the sun here. It's a similar method to Apriori, but the math is a little different, and it works better for large data sets because it's able to do it by going through the data set once to create item sets, and then it works on those. It's interpreted in the same way, and depending on the nature of your data set, specifically if you have a really large one, you may want to try Eclat instead of Apriori. Now, with either of these methods, you're going to get 3 things. In addition to item sets that say if the person bought A and B, then they also bought C. If we look at just 2 items, A and B, you get a measure of support, and that is how often do A and B appear together in the data? How often does a person get both A and B in a transaction? So you simply add up the number of transactions that have both A and B divided by the total. That gives you a proportion. That's your support. How often does it happen? And then confidence. How often does B appear when A appears? So now you're looking at just the transactions that have A. So just the ones where people bought apples. How often when people bought apples did they also buy bananas? That's confidence. It's also a proportion. And then lift gets a little more complicated. It's the confidence in the rule. If they bought an apple, then they bought a banana, compared to the support for that one item. So it looks at the confidence. That's how often did they get an apple and a banana compared to just apples, and then divide that or compare it to how often did they buy bananas overall. That's lift. And so these 3 numbers, support, confidence, and lift, are the main outcomes when you do an a priori or an Eclat analysis. And the third and final algorithm I want to mention is known as FP growth, which stands for frequent pattern growth. And what's different about this one is it uses a tree structure to represent the connections between items. And so, for instance, in this tree on the left, you have a dot that represents a specific item, and it would connect that node to the second item they bought, and it would connect that to the third item. What's interesting about this is that it uses a recursive process. So for instance, if somebody else has purchased the same pair or triplet of items, it would simply lay that over the top and count how often that pattern occurs, which is why you can get frequencies and find out which ones are the most frequent or most common. A benefit is that this recursive process allows for very efficient data compression, especially when you have a relatively small number of items and you have a large number of transactions. But any one of these algorithms is going to allow you to start mining the associations between the items in your transactions or interactions and allow you to start finding the meaning and the patterns that will be most beneficial to your organization. To begin our demonstrations of association analysis, I want to introduce you to the dataset we're going to use, which is the groceries dataset. This is a CSV file that originally comes from a package in R called A-rules, which is for association rules. Now, what's unusual about this is that it's in transactional format as opposed to a standard tabular format. Let me actually just show you what it looks like. To do this, we'll start by loading Pandas. so we can open and work with the data frame. And then we'll come down and simply open the data set. I'm going to run this one command. It's going to open the groceries.csv file from the data folder. And let's take a quick look at this. What it shows us is a number of transactions, and it starts at transaction 0. And it shows us that the first thing this person purchased was citrus fruit, then semi-finished bread, then margarine, then ready soups. And then after that, it has NaN for not a number. And it fills that in until we get to the index 31, which is actually the 32nd item. And so you can see, for instance, that we actually have 9,835 rows of data. So almost 10,000 transactions, 32 columns, or 32 different items that people could have purchased. And note that it's not the same items listed in each of these. That's what makes it transactional. It's listing as it goes across the things the person purchased. Now, you'll see that one of the analyses that we're going to do uses the data in this format. Another one, we have to clean it up a little bit by getting rid of the NaNs and put it into list format. Another one puts it into the standard rows and columns of a spreadsheet. And we'll do that transformation as we get to each of the algorithms, but this will get us started with association analysis or association rule mining in Python. By far, the most common method for association analysis is the a priori algorithm. To do this in Python, we're going to have to download a special package called Apriori. And you can download it, possibly with this, uncomment it, or I had to use this command down here. Again, uncomment the 2 lines, run them. It only needs to be done once per machine, and I've already installed it. But once you have Apriori installed, then we'll come and load these additional libraries to work with data. And then we're going to use the groceries data set that I showed you before, but Apriori needs it in a list format. So what we're going to do is we're going to create an object called transactions, and then we're going to go through the groceries data set, and we're going to take each line in that. We're going to split the cells and put commas in between them and get rid of the NaN or not a number. And then append that, and we'll take a look at the first few items in that list. So I'm going to run that cell. And now you can see it's a plain text list, and it shows that the first transaction included 4 items. The second transaction included 3. The third item had just whole milk. But this is the format we need for this particular implementation of the a priori algorithm. Now let's come down and actually apply the algorithm. There's a few things we need to specify. We need to tell it where the data comes from, and we saved it into transactions. We need to give a minimum level of support, and that has to do with the proportion of how often items occur in the entire transaction list. We're choosing a small number, 0.001. You can manipulate that to something else if you're taking too long or feel like you're missing things. Also, the minimum level of confidence, which I've set to 0.10. Again, that's one of the conditional probabilities that goes into association analysis. We're specifying the minimum length and the maximum length. You can change these, but it will affect the processing time that's involved in your analysis. And then finally, we'll print just the first rule that we get from this analysis. And what we get here is this one item, bottled water, and it tells us how often it comes in and gives us a number of statistics that are actually kind of hard to read. So what we're going to do now is we're going to convert those rules. That's just the first one, but there's a lot of rules. We're going to convert them to a table that's easier to read. We do this by going through and reading the rules and putting them in these various columns, dropping the NAs, and let's see what that looks like. Now what this shows us is that when a person buys bottled water, there's a certain probability that they will also get instant food products. The support is 0.001, the confidence and the lift, which again are conditional probabilities. Now this is helpful, but this isn't the most important rule at the top. Plus, it'd also be nice to have some of the number of observations that fall into each of these. So what I'm going to do is we're going to add the ends, the sample sizes, and we're going to reformat the list to put the items with the highest support at the top. We'll run through this cell, And now we have a table that's much easier to read and more informative. So the rule with the highest level of support of all of the rules we got is if a person purchases other vegetables, then there's a high probability that they will purchase whole milk in addition. And we have the support, the confidence lift, and the ends at the end. But maybe an even better way to do this is to plot it. And we have a slightly complicated bit of code here, but what it's going to do is it's going to produce a graph that connects different items. So let me run this code. And here is our graph. The first item, the from or A, is here on the bottom. So for instance, here is other vegetables. That's the one we had with the highest level of support. And then the second or right-hand item, sometimes called B, is here at the top. And the color indicates the level of support, where dark purple is the lowest and green and yellow are the highest. You can see, for instance, that the other vegetables, we've got a green line connecting it to whole milk. And that lets us know that that one has the strongest level of support. So this is a nice way of looking at a number of rules and seeing how they relate to each other, as well as having their support. And that's going to be our best bet for starting with association analysis in Python. The a priori algorithm may be the most common for association rules mining or association analysis, but an important second is Eclat, which is especially useful when you have large data sets. And it produces output that looks very similar, but the method in which it goes through the data is rather different. But let me show you how to do Eclat here in Python. We're going to begin by installing a package called pyeclat that allows us to do this. This only has to be done once on a machine, so I don't need to do it right now, but either uncomment this cell and run it, or I needed to run this cell. You uncomment the 2 lines and then run it. It'll install the library. Once you have that, though, you can install these extra packages, and then we can load and prepare the data. Now we're going to use the same groceries data set before, but we're going to use it in a slightly different format. What we're going to do is we're simply going to read the data set as it is. So this is the format where we use the data, where it has all the NANs for not a number, where that should be a blank cell. They didn't purchase any more items. When we did a priori, we had to strip those out and put it into list format, but we can leave it exactly this way for Eclat. Now, when we come down to Eclat, we get to specify a few parameters. For instance, the minimum level of support. This time I'm going to 0.03. You can try something else. We had 0.001 when we did a priori. And then the minimum combination and the maximum combination, I've set both of those to 2. Again, you can try different values. It will affect the processing time, so don't make huge changes without testing it first. And then we're going to have the separators and get some updates on the processing as we go through. So I'm going to run this cell, and we get this that makes it look like there's an error message, but it's just showing us how it's going through the data. Now, on this computer that I'm using, it takes a few seconds to run through the algorithm. If I were to change max combination to 3, it takes a few minutes. If I change it to 4, it takes a super long time. You can go out and get your lunch. But here we did it in 9 seconds. And let's take a look at the supports. These are the support levels for the different rules. And so, for instance, we have other vegetables and yogurt. There's its number, and then whole milk and its number, so on. This is the data that we need, but it's not in the most readable format. So let's come and convert the rules to a readable format using an approach similar to what we had before. We're going to go through this list and we're going to split it and create a table. Let's take a look at that. Now you see that we have from, or the left-hand side, if they bought other vegetables, then they bought yogurt with a certain probability. On the other hand, it's helpful to have the ends, the sample sizes, and it's also helpful to sort the rules by, for instance, their level of support, which we'll do with this code right here. This gets it into a more useful format, where again, we see the rule that occurs most often in the data set is other vegetables is associated with the purchase of whole milk. There's our level of support, and then our sample sizes. You'll notice, by the way, these numbers are a little different than the ones we got with a priori. That's because I set the parameters different, especially the minimum level of support. Finally, we can plot the rules in Eclat the same way we plotted them in Apriori. It's a very similar process. We run this box of code. It's a little complicated, but what it does is it produces a graph that shows the left-hand side or the first item here on the bottom and the right-hand side or the second item here on the top, again colored by their level of support. Dark is close to 0, green or yellow is close to 1. And you can see we have one here, other vegetables. There's a green line. It goes up to whole milk. And again, that's a good way of going through a large number of rules and getting a quick, big picture impression of what you're dealing with to help direct you as you try to get actionable insights from your association analysis using the Eclat algorithm. The final method of association analysis I want to demonstrate is called FP growth, which stands for frequent pattern growth. And again, while a lot of the results are going to look very similar, this goes about the process in a dramatically different way by creating frequent pattern trees. And it does it in a way that can make the processing massively more efficient when you have data sets that have repeated patterns of associations, because it simply creates the association once and then counts when it happens again. To do this in Python, we're again going to have to install a new package. This one's called mlextend for machine learning extend. You can either run this command, uncomment it and run it, or this one, I had to do this one down here, uncomment those 2 lines and run them. It only has to be done once per machine. And once we've got that loaded, we can get the data. What's funny is we do it in a slightly different way. Let's first get the data, the groceries data set, and read it as this list. So we've gotten rid of the rows and columns. We've gotten rid of the NaN for not a number for the missing cells. But then we're going to have to actually get it into standard spreadsheet format. And we'll do this with this little function. We're going to do transaction encoder, and we'll save it to df. But now you see we have the way you would normally set up a spreadsheet, where you have each item listed on the top and simply a true or false as to whether that transaction included that item. Most of these are false, but you can see a few over here that included whole milk or that included yogurt, and that's it. So for our 3 different algorithms, we set up the data in 3 different ways. It's just a matter of the implementation in each of the different packages. Now we're going to get the rules. We're going to build the rules. By going through the algorithm, we specify the minimum level of support. This time I'm using 0.01. We're going to use the column names for the items, and we specify the maximum length, which I'm leaving at 2. Then we go through and create this list of rules. Let's run through. And we've already created a table here, and it's in a slightly different order than what we've had before, where you see the support here on the left. Then we have whole milk and other vegetables. Those are the 2 items in the item set, but the predictor, the left-hand side, is whole milk, and that goes to other vegetables, and it tells us how often that occurs in the data set. Now let's reformat that a little bit so we can order it by support and add the ends. This is something we've done before. And here you see from whole milk to other vegetables. This is a way of getting the information we need. And we can also graph it just as we've done with the other methods. We'll come down here, we'll run through this code, and we'll produce a graph that shows the left-hand items, the from on the bottom, the right-hand items or 2 on the top, and then the support is indicated by the color. And so this is one more method you can have in your toolbox when doing association analysis. Again, can be helpful when you have a very large data set with repeated patterns of associations. But any one of these is going to get you started on mining the connections between the items that you can use to find value in the work that you do for your own organization. Now that we've looked at 3 different algorithms for association analysis, it's time for you to get a little bit of hands-on practice. And to do that, I want to give you this challenge of applying Apriori to a new data set. What we're going to do in this challenge is use a data set called epub.save. That's for electronic publication. And it's in our data set folder. And I want you to take that, import it and prepare it, apply the a priori algorithm, list the rules in a readable table, and plot the rules. To do this, you'll need to have the a priori algorithm installed, just like I did in the demonstration of a priori. But let me tell you just a little bit about the data. It's a transactional data set like we had with groceries, where it shows for each transaction the items, in this case, electronic publications, that people requested in a particular transaction. Now, this one's a little different from the groceries in that it doesn't have NaN or not a number for the blank cells. That makes the data file much smaller. But otherwise, you can implement it in the same way that we did with the groceries data set. I invite you to take a couple of minutes to run through and do the a priori challenge on this data set. Then come back here and we'll compare our responses to this challenge. Hopefully you've been able to take a few minutes and work through the challenge of applying the a priori algorithm to the EPUB dataset. I want to show you how I solved it, and you'll see that it follows the pattern of the original demonstration we had on a priori. To do this, once you have the a priori library installed, we're going to load a few libraries and algorithms. Then we will load the data set, and we're going to do it in the list format where we show the things that people put down here. Now, this is actually 3 different transactions. It just happens to be that each transaction includes just one item. And all of them go by document, and then an ID, 154, 3D6, 16F. These are ways of identifying the documents. Again, the first 3 transactions each have just one item, and these are those items. But let's apply the a priori algorithm to this data set. To do this, we set minimum support, minimum confidence, minimum length, and max. And I'm using the same values that we had in the a priori demonstration. And from that, we get our first rule that involves these 2 items, doc11D and doc6BF. And it's kind of hard to read all of this, so we're going to convert the rules to a readable format or a table with this cell right here. From there, you can see from document 11D to 6BF, we have the support, the confidence, and the lift, but it's better to reformat that. So we have additional information with the from N and to N, the sample sizes, as well as sorting the association rules by their levels of support. And what you can see on this one is that the one that has the highest level of support is this first rule. Again, these are cryptic names, but it lets you know that this was the one with the highest level of support. That said, it's a very low level of support, which means there were not an enormous number of repeats in terms of the documents requested from this data set. But we can also come down and we can plot this one. And I can tell you this one's going to look a little different because there are so many different items involved. But what this gives us is a chart with the from item listed on the bottom with their little cryptic names and the 2 items listed on the top. And you can see there are some repeats in terms of things leading to the same item on the top and the bottom. They all have pretty low levels of support because there are so many different things in this transaction. But this is a great way to get started, potentially to do something like building a recommendation engine. If you requested this one, you may want to request this one as well. That's one of the goals and the benefits of association rule mining that allows you to find these common patterns and potentially work with your clients and help them find the things that are most important to them. Perhaps you've seen on an old clock the saying tempus fugit, Latin for time flies. And that is at the crux of an important issue in analyzing temporal data. The idea is that it doesn't stay still, it's moving, and the problem is it's only moving in one direction. Time only moves forward, and that gives you special analytical challenges. Fortunately, there are several methods within analysis in general, and data mining in particular, to deal with this temporal orientation of time-based data. The first one that we're going to look at, and the most basic, is called decomposition. It's like taking that phone apart to see what it's made of. With decomposition, or uncomposing, taking apart, you're going to separate time series data into several elements: a smooth trend, seasonal variation, and noise that's not adequately explained by those other two elements. Time series decomposition is generally a descriptive procedure. It's a way of getting a big picture of what's going on. The nice thing about it is a visual procedure. It gives you a graph that's very clear and easy to see what's happening. Also, you have some choices. You can have additive models for things where forces accumulate over time, or multiplicative models where you're looking at things like rates of change over time. And I'll demonstrate both of those. Another very common method for working with temporal data is ARIMA. I like to think of this as looking backwards. ARIMA is a portmanteau for autoregressive integrated moving average model. And here's what each of those things mean. The AR, the autoregressive part, means that later values are predicted by earlier or lagged values. To lag means to go back one step in time, or two steps, or three steps, to try to predict what happens later. The I in ARIMA is for integrated, and that means that the absolute values in your data are replaced by differences in the data. So for instance, sometimes when they report stock market prices, they'll tell you what the value is today, but then they'll say how big the change is from yesterday. That's the difference, the integrated part. And then finally, the MA in ARIMA stands for moving average, and that's where the regression errors are linear combinations of current and previous values. Please note, this is not to be confused with the standard moving average, which is used to smooth time series data. It's a moving average model. It's a little more sophisticated. Now, there are lots of variations on ARIMA. There's ARMA, which doesn't have the I for differencing. There's SARIMA, which includes seasonal components. That's actually what I'm going to demonstrate. And many other things that allow you to stand where you are, to look back and use that to predict the future. Finally, we're going to look at something called MLP, which stands for multi-layer perceptron. And that's an entire class of feed-forward artificial neural networks. And neural networks have been where so much of the amazing developments in data science have been. A neural network is designed to have an input layer, which you see here on the left, one or more hidden layers, which you see here, the second and third columns of data, and then an output layer, which gives you the prediction. Now, the nice thing about MLPs is while they're based on, regular perceptrons, they do several things. Number one, they can have several layers. We're going to demonstrate that. And they can also have what's called a nonlinear activation function. One of the benefits of that is it makes it so that MLPs, like several other kinds of neural networks, can distinguish non-linearly separable data. Another example is a recurrent neural network, or RNN, that's also frequently used, but MLPs are a little more flexible and apply very well to the data that we'll be demonstrating. But any one of these approaches, the descriptive practice of decomposition, the ARIMA class of models, or a neural network like MLP, will give you a great way to find meaning in your temporally structured data that is always moving in one direction towards the future. Time series mining is a special kind of analysis for a special kind of data. And to demonstrate the algorithms that we'll use, I want to show you the air passengers data set. Let me begin by importing a few libraries. And then the air passengers data set comes from a well-known book from the 1976, but this gives us monthly data on the number of international airline passengers in thousands from 1949 to 1960. So it's a long time ago. These weren't huge numbers, but you can see the increase overall and the variation. So this is a great example of doing time series analysis. I've saved the data as a CSV file in our data folders. It's called airpassengers.csv. And we can see the raw data by just reading it this way. And you can see we have here the month, and we have the number of passengers in thousands during that month. So that's the basis of what we're starting with, but we do need to do a little bit of preparation, in part because by default, Python doesn't necessarily read months as dates. And that's an important thing for time series. So what we're going to do is we're going to read the data again. We're going to parse the dates as a month and then tell it that the index column is month. Save that to DF for a data frame and then look at the head. And now we can see it. It's formatted a little bit differently. We now have the month here on the side and the number of passengers right there. We can also get basic descriptive statistics for this. And it's going to just do passengers because the other one's like an index column. And so we have the mean, the minimum, the percentiles, the maximum. But the best way to look at time series data is by plotting it over time. And we can do that pretty quickly with this set of commands. And here's where you see starting in 1949 and going up to 1960, you can see that it's increasing over time, but also we have a dramatic seasonal shift. It looks like maybe people travel more during the summer than they do during the winter. But the point of the analyses we're going to do is going to find ways to predict patterns, even with this strong seasonal pattern. And so let's take the air passengers data and start looking at ways to do time series analysis in Python. One of the best ways to start working with time series data is not to start modeling it immediately, but to start describing it and doing a very simple kind of analysis. Remember, analysis means to break things into their constituent components. And what we're going to do is called time series decomposition, where you are taking it apart. You are decomposing it into its elements. One of the great things about decomposition is that it's visual. And so let's start by importing a few libraries, including stats models, which will give us the seasonal decompose function. And then we'll import our data set with airpassengers.csv saved locally in our data folder. And we'll plot the data as it is. And so what you see here, again, is the strong upward trend in the number of air passengers year to year, but also a strong seasonal trend where it's higher in the summer and lower in the winter. What we want to do now is separate the linear trend going up from the seasonal variation and also any other random noise we may have from one year to another. So what we're going to do is we're going to come down and decompose this. We'll start by simply setting the figure size and then running a very simple command, seasonal decompose. We say where the data is, it's in DF. You need to specify the period. How many observations are there before things repeat? Because we have monthly data, we're going to have 12 periods before it repeats the yearly cycle. If we were measuring quarters, then that would be 4. If we were measuring days, it'd be 365. And so you simply need to specify how many times it goes through before you expect it to repeat. And we can run that plot. And what we have here are 4 plots. This is simply a shorter version, less tall version of the original data. And here you see a smooth general upward trend for the number of passengers over time. Below that is the separated seasonal component. And by the way, you'll notice what it does is it does it exactly the same every year because it's predicting, it's based on the assumption that the seasonality is consistent from one year to another. You can see that it goes up in the summer, comes down in the winter. And then this last one with the dots is the residuals. This is what's left over. Now, what we've done here is called an additive model. And the idea is that for a given year, you take where it is on the trend, you add the number here on seasonal variation, which goes from plus 50 to negative 50, and then you add the residual, and that will give you the sum total that you have in this line. On the other hand, there is one thing. We have data that is heteroscedastic. It spreads out, it fans out over time. And you can see that in the residuals, it goes way up and way down. That suggests that maybe instead of an additive model, we should use a multiplicative model, which is able to have a consistent percent change at each step. All we have to do for that is add this one argument, model equals multiplicative, and we can plot it. The top is the original data, looks the same. The trend looks very similar. The seasonal variation resembles what we had before, but now instead of being numbers that are added, these are coefficients and you multiply the trend by that number. And then the residuals, instead of being centered around 0, which is what you would expect if you have an additive model, are centered around 1, which when you multiply it times 1, it means you don't make any changes. But now you can see that the residuals are very, very tight and consistent over time. And so this suggests that a multiplicative decomposition is more appropriate for something that changes as a percentage over time, which seems to work best for our air passenger travel information over a period of years. When working with data over time, decomposition, which I showed you earlier, is a great way to visualize the general pattern of what's happening. But to make specific predictions, you're going to have to do something more sophisticated than that. And one of the most common approaches is ARIMA, which is a portmanteau for autoregressive integrated moving average. To do ARIMA in Python, you're first going to need to install a new library, PMD ARIMA. Now, you only have to do this once on the machine. You might be able to do it by uncommenting this code and running it. Or in my case, I use this code. I uncommented that and ran it. But let's load the libraries and special functions here. And then let's bring in the air passengers data. We can plot the data overall. This is the entirety of the data, but we're going to split this data into a training and testing part, which is especially tricky when you're looking at changes over time, because you don't just do random splits. You take data that occurs before a certain time, that becomes the training, and data afterwards becomes the testing. So we'll use 1949 through 1957 for training and 1958 through 1960 for testing. We do that here by creating the training data, and we can plot the training data. You see, it looks very similar. It just stops 3 years early. The testing data, we do a similar thing. And we can plot that, and you see a pattern of just 3 years. By the way, the vertical scale has changed because it's at the higher end, but you see the pattern overall is very similar. Now we can do some of the background work for ARIMA. One of the things we have to do is test stationarity. ARIMA requires non-stationary data. That means that there has to be changes in the mean, the variance, the covariance over time, and that you show correlations at later times to earlier times. The easiest way to do this is to look at a graph where we're actually going to run a number of lags, 24 lags. That means we're going to correlate this month with the last month, and then this month with 2 months before, then this month with 3 months before. Those are the different lags, and we're going all the way back to 2 years. And what we're trying to find are lags that are statistically significantly correlated. And those are going to be the ones that are outside of this blue range. And what you see is that the first 12 have autocorrelations, meaning again, correlated with previous observations in the same time series. But then after that, they go down to noise. This is going to be what we need as long as we keep the autocorrelations to less than 12. Now, as a frame of reference, we can do a linear regression model, and it lets us use the time to try to model passengers. Here are the regression results. You can see the slope and the intercept right here, but it's going to be easiest to get the fitted values, get the confidence, and then we come down a little bit, graph the entire association. So what you see here is in black is the time series data that goes up and down. The linear regression line is a straight line by definition, and we have a confidence interval that goes around it. And it's really good at capturing the general trend, but it would be horrible for predicting actual values because it doesn't get any of the seasonality in it. And that's why we need to go to ARIMA. Now, the easiest way to do ARIMA is to use the auto-ARIMA function. And what we need to do here is tell it how frequently things repeat. And we're telling it m is equal to 12 because we have 12 months to each year. So let's run that, and it's going to tell us what are the best parameters for the ARIMA model. And by the way, you'll see here, it says that we have not ARIMA, but you might say Ceramax results. That's because this is the seasonal autoregressive integrated moving average with exogenous factors. It's a lot of words there. But the important part is right here. This is the model where we have two sets of numbers in parentheses. Now come down here. The first set of numbers is for the basic non-seasonal model. They were just something increasing over time. The first number is the autoregressive order. The second one is the degree of differencing. That's the integrate. And the last one is the moving average order. And it says we should use 1, 1, and 0. The second set of numbers is for seasonality, where again, we have the autoregressive order, 0 in this case, D, the integrate or differencing, 1, the moving average, 0, and the model period or seasonality is 12. That's probably the most important one right there. So we can run that. There we get those, and then we get the next set of numbers. But we can get the residuals from our model, the things that are left over after it predicts it, and we can plot the standardized residuals. The good news is that after the first month or so, they kind of settle in around 0. So it looks like our model is predicting things well in the training data. And then we can also get the autocorrelation function, the ACF, of the residuals. And what you see here is that nearly all of them are in the region of non-significance. So they are not statistically significant. That's a good thing with residuals. It means they're all pretty close to 0, aside from this very first one. But this is what you normally are looking for. One more diagnostic test that you can do is the long box test for autocorrelation. We're going to run that one. And mostly we just want to see that the p-values are greater than 0.05. That means that they are not statistically significant. And so this is in fact what we were looking for. But now we can actually test the model. What we're going to do is we're going to find the best model for the training data. There we have it right there. And then we're going to get predictions for that. We'll extract the time series of model predictions to get predicted values, and we'll get prediction intervals, confidence intervals. Probably the single most rewarding part of an ARIMA model like this is the graph of the predictions. And so what we're going to do here is we're creating a graph and we're overlaying the individual predictions and the prediction intervals. And we run that. And you can see right here, we have our up and down trend over time. Our training data stops right here at 1958. And then 58, 59, and 60, we're trying to predict what would happen in those. The forecast is the red line going up and down, and these light blue are the confidence intervals. But the actual observed data for that time is in a dark blue line. And you can see we have fabulous predictions, both with the general upward trend and with the seasonal variation based on the ARIMA model that we did. Now you can also save these values, and you can see the predicted values that are used to create the graph here. But the point of all of this is that ARIMA, which is a rather sophisticated approach, is able to capture both the general upward trend as well as the dramatic changes in seasonality, and do it in a way that can make very accurate predictions. So much of the progress in data science and in artificial intelligence over the last decade or so has been through the advent, really, the practical development of neural networks. And one kind of neural network that can be very useful for time series data is MLP, which is for multi-layer perceptron. Now, you can also use others like a recurrent neural network, and these work in ways that are really somewhat mysterious. They're very complicated in how they work, but in certain situations, they can be remarkably accurate, especially with very complex data. Now, what I'm going to show you here is there's a fair amount of custom code here because there's not quite the functionality I would want in packages yet, but I like to think it will arrive soon. And because there's so much code, I'm going to be going through it rather quickly, but you'll be able to explore some of this as you have more time and more interest in it. I'm going to begin by importing a number of libraries and then importing the air passengers data CSV file from our data folder. We'll plot it. There's the same pattern that we've seen several times. Now, for the algorithm that we're going to use, we need to reshape the data into a matrix. And I'm going to do that by setting K, which has to do with the number of months in our seasonal cycle. And it's this matrix that we need for working with the MLP. One of the other things we're going to do is we're going to split the data. And in this case, we do an 80% training, 20% testing. And then we rescale the data to standardize things to make them more consistent. And we extract the features, that's the first 12 columns, from the target, the last column, in our new matrix. We can plot the normalized training data, and you'll see this looks very similar to what we had before. The big difference is here on the side. Instead of saying how many thousands of passengers there were each month, it has a mean of 0 and the standard deviation of -1, +1, +2. And we do a similar thing with the normalized testing data. Again, what we have are z-scores over on the side, and all of these are above the mean that we have elsewhere. Now we're going to fit the multi-layer perceptron, the MLP model, using the 20% validation set we created. I can run that, and then we can use the mean squared error, or MSE, for a way of measuring validation loss. We can calculate that and see how many different hidden nodes we should have in our model. What we're trying to do is reduce the mean squared error. We want to be low on this graph. And as a function of hidden nodes, you can see right here, 25 is the lowest one there. And we can actually ask it to print that for us. It says 25 is going to work the best. And then we can apply a model with 25 nodes to our training data. And then we can use that model to forecast the test data, the last 3 years of the air passenger information. And because we had converted things to standardized scales, which were necessary for this algorithm, we're now going to convert them back to their original scale, which is thousands of passengers per month. And then we can plot that using the original training data, the testing data, and our forecast in the original scale. And what you see here is in black is the original training data. In red is the forecast based on 25 hidden nodes in our MLP neural network. And then below it in dark blue is the test data. It's almost a perfect match. This is wonderful performance for a very simple neural network. But I want to show you another way of doing this instead of the 80-20% split, and that's using fivefold cross-validation. And so I'm going to set this up with 5 splits. We'll again use the mean square error as our method for assessing cross-validation loss. And really, you want to plot it so you can see what the options are. And in this case, using this other method, it says that 50 hidden nodes would be most effective. We get that right here. We get the 50. And now we can create a new MLP regressor using those 50 hidden layers. So we'll run that through. We'll get our predicted values. And then, as we did before, transform the data back to the original scale. And then the payday here is with the graph that once again shows the training data in black, the testing data, the true values in blue, and our red forecast data is almost exactly on top of it, getting both the general upward trend and the strong seasonal variation. Both of these mean that MLP, as one common form of neural network for time series data, can model complex shapes over time and can be a useful addition to trying to make sense of those complex patterns in your data. I want to give you a challenge where you can actually take some time series data and analyze it using some of the methods we've looked at. Specifically, I'm going to give you a time series and ask you to decompose it into general trend and to seasonality and to see what kind of insights you can get from that. To do this, we're going to use a new data set called eustockmarkets.csv. It's saved in our local data folder. I want you to import and prepare that, plot the data, and then do both an additive decomposition and a multiplicative decomposition of the data. Now, let's import a few libraries so I can show you the data and set this up for you. This data set is financial data, which often grows at an exponential rate. It comes from the R package EU Stock Markets. It's saved as a CSV file, and it gives the daily closing price for 4 major European stock indices: German's DAX, Switzerland's SMI, France's CAC, and the UK's FTSE from 1991 to 1998. However, I've done two things. Number one, because decomposition is easiest with just one time series as opposed to four, you can do four, it's just a lot more complicated. I included only one, France's CAC for Cotation Assistée en Continu, or Continuous Assisted Trading. Second, to make this more similar to the earlier demonstration of decomposition, I've included data from just the last trading day of each month as opposed to every trading day. That makes it monthly data, follows the same pattern we had before. So I'm going to import the data with this command. We're going to read CSV from the data folder EU stock markets. We're going to parse dates and the index column. When we do that, we see the months listed here and then the CAC values here on the right. So I want you to take those and do a decomposition, and then we'll compare responses to this challenge in just a minute. Let's take a minute to do the time series decomposition challenge together, and I'll show you the solution that I have, which is based on the presentation of decomposition we had earlier. I'm going to start by loading some common libraries and then bringing in the data eustockmarkets.csv, and we'll take a look at the first few rows. So we have the CAC information, which is from France's stock market, and we have the month, and we can plot the entirety of the data. And so what you see is a change over time. It's going up, it's going down, it's going up, it's going down, and then it goes way up, about doubles in value in a couple of years. So this does not show the same steady, predictable trend and seasonality that we had with our air passengers data, but it is the kind of data that many people are intensely interested in looking at. So let's decompose it and see if we can find something useful in here. We'll begin by doing an additive decomposition. All we need to do is make sure that it knows that we're doing 12 months in a cycle, because the idea is that it's going to repeat in a similar trend year after year. So let's run that one. And what we see is our original data, the general trend, which goes up, goes down, and then goes up again. The seasonality, which again, by the way the formula is created, is made consistent over time. And then the residuals, you can see that they drop a little bit here at the end. Now, because this is growth over time, financial data is often grows at a set percentage over time. A multiplicative trend may be more appropriate. And we can do that with this one line, simply making sure to have multiplicative under model. And now we have the original data, the general trend, the seasonality, which again, now these are coefficients that you use to multiply these numbers. And then we have the residuals, which from here appear to be a lot more consistent and probably better match the original trends. And so this is one way of taking a new method you may have learned, decomposition, applying it to a novel data set of something that a lot of people care about, and that is financial changes over time, to get an exploratory view of it, see what's going on there, and guide you in your further analyses. Text is not like other data, and when it comes to data mining, it poses some very special challenges. Those challenges include things like the fact that there are enormous quantities of text. There is so much open text in terms of books, in terms of news articles, and in terms of social media. It's completely overwhelming. Also, it's enormously variable. There are so many different words, there's so many phrases, there's so many misspellings and colloquialisms. There's a lot there. What this all tells you also is that it's unstructured. It doesn't fall into nice little rows and columns of data. It just kind of is what it is. That makes it a very difficult thing to mine for. And when you're mining for data, you're trying to get value. You're trying to get more than like Hamlet saying that he is reading words, words, words. You're trying to get meaning and actionable insight out of your data. Now, there are three ways that I can think of that data mining with text is particularly important. One application is in modeling topics, where algorithms are used to say what a news article is about, or what the topic of a social media or blog post is. Another one is summarizing content. Can it take an entire scientific article and boil it down to a paragraph? Or can it take a text of a political speech and reduce it to a few sentences that have the essential meaning of it? And then another one is classifying text, taking unstructured text and putting it into nice, neat groups. The prototypical example is the spam filter, but anything that sorts the data is going to be enormously useful and save a lot of human time and effort. In the demonstrations that we're going to look at, I'm going to focus on another element of text mining, which is called sentiment analysis. This is where you're trying to find the emotional content of data. And the place where this is really significant is in online marketing. You want to know if people are saying positive or negative things about the product or the service you're offering. That allows you to tailor both the product or service you offer, as well as the appeal that you make and who your audience is. We're going to start by looking at binary sentiments. And this is where you're simply looking at whether somebody says something that is positive or negative, this or that, either or. Now, to do this, it's not like you sit around and decide whether somebody's positive or what. You use a published lexicon. This is some information you import into your computer program. That's a list of words and their associated sentiments. Now, what's nice about this is simply categorizing things as positive or negative. It's by far the quickest and the easiest analysis of sentiment in text. If you want to go beyond that, and I'm going to go beyond that, you can also look at the scoring of sentiments. And this is not just positive or negative, yes or no, but it's where words are scored by the strength of the emotions. For instance, we're going to use a -5 for most negative up to +5 for most positive scale. And what you're relying on here is another lexicon. This time it has associations for individual words. And the fact that they're individual is important. It's looking at one word at a time. You can develop other systems for looking at associations between the words, or for instance, a negation of a topic, or a phrase that has a double meaning. In fact, that gets us to the final thing I want to look at, which isn't sentiment analysis per se, but it's word pairs or the association between words. It answers the question, which words go with which ones? And are there unexpected associations in the text? It's like trying to sort through with your socks and see this goes with this goes with that. And is there a predictable structure to your data? And what you'll find sometimes is that different texts pair things differently, that they tend to use it with a negation, or they tend to use it in a positive or negative way. In the demonstrations we will look at all three of these methods for finding meaning in unstructured text. We'll look at binary sentiment. We'll look at scored sentiment, and we'll look at the structure of word pairs through visual methods. And all of these can get you started on finding useful and actionable meaning from your text. Text mining is just a whole different kind of data science, and consequently, we're going to be working with a different kind of data. To introduce us to the section on text mining, I want to show you the data set that we're going to be using, which is the text The Iliad by Homer, written forever ago. We're getting the Iliad from Project Gutenberg, which provides over 60,000 free ebooks. There are a lot of other options there, and we'll try some for the challenge, but right now, let's use the plain text version of the Iliad that I've already downloaded and saved for us in our data folder. All we need to do to see this is to import Pandas, and then we're going to read CSV, but we're actually reading a text file. And we're going to separate things. We're going to drop the empty lines, and we're going to remove what's called the Gutenberg ID. And we'll look at just the first 10 lines, and what you see is the title page of this edition of the Iliad, rendered into English blank verse by Edward, Earl of Derby. And this is where we're going to start for doing text mining in Python. The first kind of text mining that we want to look at is what I'm calling binary classification of sentiment. And what that means is looking at the words in the text and deciding if they are either positive or negative. So simply those two categories, positive or negative, without quantifying the degree. That's something we're going to do in a later example. But let me show you how this works with the Iliad. First thing you need to do is you are going to need to install a library NLTK for Natural Language Toolkit. You might be able to uncomment this command and run it, or in my case, I had to uncomment these 2 lines and run those. But once you have NLTK installed, then we're going to load a bunch of libraries. We're going to bring in regular expressions, NLTK, some plotting and pandas, and then we're going to bring in some corpora. These are things that let us know what certain kinds of words are, both how to split words up and whether they're positive or negative. And then we have to bring in some data as well. And then we're going to bring in a matplotlib style sheet. So let's run all of that. And then we'll import the data. Again, this is just a text file. It's Gutenberg. And we're going to split things up, and we're going to drop the blank rows and drop the ID. And we'll take a look at the first 10 rows. Great, and that's what we've seen before. Our next task is to tokenize the data, which means to split it up into pieces. So instead of sentences and paragraphs, we want individual words. We're going to convert it to lowercase. We're going to get rid of anything that's not a letter or a word, get rid of extra space, and so on. And then we'll split it into the individual word tokens using the word tokenize function. We'll take a look at what we have at the top then. And here you see the individual lines split into separate words, the, comma, Iliad, comma, and so on. Now what we're going to do is we're going to collect these into a single series, because you see right now we have several words in each line. Now we have the on its own line, Iliad, and so on and so forth. The reason we do that is because then we can sort it. We can count how often each word happens, and we can get its frequency and sort it by frequency. Now, in certain situations, you can actually stop here. Simply knowing what are the most common words, probably as a proportion of the overall length of the text, can be informative in and of itself. But right now you see that our problem is we have words like the, and, of, to. I do know of analyses that use these kinds of words as their central point, but those are called stop words, and they're generally not considered really informative. And for a sentiment analysis where you're looking for positive, negative, they're not helpful. So what we're going to do is we're going to remove all of the stop words by bringing in a stop words set and then taking them all out. Then we'll look at the revised tokens by frequency without the stop words. Now you can see son, thou, thus, thy. Again, this is a very old text, so we have the archaic English. But at this point, we can start classifying the sentiment. We're going to look for valenced words, things that have an emotional element to them, with the opinion lexicon. So we're going to find words that are positive, and we'll count those. We're looking at opinion underscore lexicon positive and negative. Then we'll drop the words that are not in either of those lexicons and take a look at what we have. And now you see we have modern, success is positive, well is positive. We have urgent is negative, regret is negative, and those make sense. What we can do now is simply count how many positive and negative words there are and look at the relative frequency of the two of those. So we're going to take the token value counts, take a look at the top 10. Well happens 279, death happens 236, and now we can summarize those. Let's get a quick summary. We have 6,387 negative words. That as a proportion, 0.552 or 55.2% of the valenced words. And positive is slightly smaller. And even easier, we can make a bar graph of that. And there you go. What this tells us overall is that the Iliad has more negative words than it does positive words. Not an enormous difference, but considering this is a war story, this is something that makes sense. And that's the first kind of analysis we want to do. Simply breaking down the individual words, counting how many are positive and counting how many are negative. It's a great way to get started with insight in text mining in Python. If you've studied literature, you may know about the narrative arc. It's a very common pattern of the progress of the action or the emotions in a story. One of the really neat things about sentiment analysis is we can actually get a visualization of the narrative arc, at least the emotional content, in open structured text. To do this, we're going to be scoring the sentiment. That is, we're going to be putting number values, not just whether it's positive or negative, but how positive and how negative. Let me show you how we can do this. First, we're going to need to load a new package called afinn, A-F-I-N-N. And you can either uncomment this command and run it, or uncomment and run these two commands. That's what I did. But once you've installed afinn, then we'll load a number of libraries, including afinn for our sentiment values. We'll import the data. We're using the Iliad. There's the imported text, the way we've seen it before. Now we're going to do something a little different. We're going to add line numbers. And the reason we're doing this is that allows us to keep track of where a word comes and then see where it falls in the arc. So let's do lines. And now you see the line number here on the end. Now we'll tokenize the data. Again, we convert it all to lowercase. We get rid of everything that's not a letter. We split things into words. And there's our tokenized data along with the lines. Now we're going to collect it into a single series, just one word at a time. There we go. At this point, we can score the sentiments. We're using the afinn lexicon, scores words from -5, most negative, to +5, most positive. And because we're not concerned about words that have no emotional valence, we'll drop anything that has a score of 0. So we'll have only positive and only negative numbers, but we'll know how positive and how negative. So once we score that, we can get a table that shows that there were 12 words with a score of -5, 9 with a score of -4. On the other hand, there were thousands between -2 and +2. A better way to look at this is to graph it. So let's take that information and let's create a bar chart. Now, note this is a little different from a histogram because we don't have the zeros. I've left those out. But you can see that we go from -5 to 4, and you can see the general pattern. We have a lot of words with a -2 or a +2. So there's some valence on each of those. But if you want to see how the narrative arc, how the sentiment changes throughout the story, we can do that by taking the line numbers and then breaking the text into sections of 100 lines each. That's an arbitrary number. You can choose something else. It does not correspond directly to sections or chapters, but it's a manageable amount. And then what we can do is we can plot these narrative values. These are the average valence for each of the sections. You see it's positive, negative, negative, and so on. So let's come down here and plot the whole thing along with a moving average. So what we have are the sections, and there's about 180 something sections. So it's a good number to work with. The gray line shows the average valence or average sentiment for each section. The dark black line is a rolling average. It smooths it out a little bit. And then the red line is just a reference for where 0 is. And what you see is the Iliad hovers pretty close to 0. And then you also see that it dips down, which is something that is common in the narrative arc. You set up the story, you have a challenge, you have a crisis, you have a resolution, and then it actually ends in a negative way. This is to be expected from a Greek epic story about warfare, but it is a great way to see the change in sentiment over time. One of the things that we're able to do with text mining in Python. So far, our text mining has been looking at one word at a time, and specifically whether it's positive or negative, or how positive or how negative. But you can also look at collections of words. And one interesting way to do this is to look at word pairs. And that gives you the connections between words. To do this, we're going to start by installing yet another library, networks. And you can install it with either this command or this command. But once you have that installed, we'll load our libraries. And networks is good for installing network graphs. That is the connections between people or pieces of information. And we're going to be doing the exact same thing in this example. Let's start by importing the Iliad, which we've seen before, and we'll tokenize the data, again, like we've done before. And now what we're going to do is we're going to create word pair tokens. Again, previously our tokens or the unit of analysis have been single words. But as I mentioned before, you can do something other than single words, and we're going to do pairs. Specifically, we're going to do n-grams of 2 words. N-gram is a generic term. It means a collection of this many words where n can change. We're doing n-grams of 2, sometimes called bigrams. You can do n-grams of 3, 4, or 5 words. After that, it really does get unwieldy. So we're going to keep it to this limited number. But let's create our word pair tokens by getting n-grams of 2 words each. And now what you see is it starts with the text, the Iliad of Homer, and it says, well, you have the Iliad and Iliad of and of Homer. Those are our 3 pairs in those 4 words. Now let's sort the n-grams by frequency, or the word pairs. And what you see again is that the stop words dominate the list. To the, in the, of the. We're not really concerned about those. And we want to get rid of them, but because we have 2 words at a time, it's slightly more complicated than our stop word removal in the other examples. What we're going to do is we're going to start by splitting these pairs into 2 separate words, put them each in their own column. We'll just call it word 1 and word 2. There we go. And we can see how many there are. There's 127,000 rows right now. And what we're going to do now is we're going to find stop words in either word 1 or word 2. So if either of those words is a stop word, we're going to drop that row. And not surprisingly, we lose a lot of data. It goes from 127,000 to 33,000 rows. Still, it's enough to work with. And so here we have English blank blank verse, and we can get the number of rows. There's the 33,000. But now let's look at the word pairs and sort those by frequency, because there will be some that repeat a lot. Old man appears 51 times. Peleus's son, 51. The mortal, 44. And so on. But really the best way to look at this, again, is with a graph. So let's come down here and let's look just for word pairs that appear at least 12 times. Now, that's a word I got by doing this process several times and saying that 12 seemed to limit the amount of things we had to graph to a manageable amount. There we go. And now we can visualize the graph. And in fact, this one, we're going to restrict it to 25. And it makes a big circle and it connects the pairs of words. And so what you see here are, for instance, brass clad, let us, sun, godlike. These are the pairs that appear frequently. And from this, you can get an idea of how the sentences are constructed or the ideas that go through in the text. And this is, again, one additional way among many others of mining for meaning and getting some useful insights when you're doing text mining in Python. And now that we've finished the demonstrations for our last chapter on text mining, I want to give you one more opportunity to get some hands-on practice with one of these procedures. What I'm going to ask you to do is the sentiment scoring for a new document. And in this case, we're going to use Little Women by Louisa May Alcott. I've downloaded a local version from Project Gutenberg and put it into our data folder. But I'm going to invite you to do the same thing that I did with the sentiment scoring in the Iliad. Import the text, add section numbers to put into sections of 100 lines, tokenize the data, score the sentiments, calculate the average sentiment scores for each section of 100 lines, and graph the sentiment arc or the narrative arc of the entire story. You can follow the example of sentiment scoring from the Iliad, and then let's meet back here in just a minute to compare our responses to this challenge. So hopefully you've had a couple of minutes to go through the new text for this challenge, Little Women, calculate the sentiment scores, and then see how they change as the story progresses. This is following the example we had in sentiment scoring with the Iliad. Let me show you how I did this. I begin by importing libraries, including afin, which is necessary to get the sentiment values. Then we import the data and get the first few rows. Here we have Little Women by Louisa May Alcott. All right, now let's add line numbers. This allows us to split it into sections so we can look at progression through the story. Then we'll tokenize the data. Again, put it all lowercase, get rid of anything that's not a word, split up the words. There we go. Now we'll put it into a single series instead of little, women. There we go. Now we can score the sentiments using the afin lexicon. Again, this goes from -5, most negative, to +5, most positive, according to that lexicon. Let's get a frequency table. And we see we do go the full range from -5, although that appears only twice in the story, up to +5 3 times. But we have an enormous number here in the mid region. We can graph those score frequencies. And we see, yes, once again, we have a lot of -2s and a lot of +2s. That's something we had in the Iliad also. So there seems to be a preference towards choosing words that have moderate sentiment in both cases. But we do go the full range. But again, the most interesting thing here is to look for the narrative arc, to look at the change of sentiment as the story progresses. And we can do that by first getting sections of 100 lines and getting the average sentiment for each section. They're the first 10 sections. And then we can plot them. And here what we see, again, is from sections 0 up to about 160 something. And then the gray one shows us the average sentiment for each of those sections. The red line is just a reference for where 0 is. And then this dark black line is a moving average. It helps smooth out the pattern a little bit. A couple of things you can see. Number one, this is a positive story. Little Women is a wonderful story. And it does go up and down a little bit, but really what you can see is it starts high, well, at 0.5, and it has some up and down. We got a little bit of a dip there and there, but it ends even higher. It has a happy ending. And so this is one way of looking at the overall pathway, the trajectory of the story. And with that, we have finished both text mining and data mining in Python. So we've come to the end of data mining with R. Now where are you going to go? It's a little bit like you're getting ready for a trip. What's your actual plan? What's your map? Well, I want to make a few suggestions for both the immediate and the longer term future. For the immediate, I recommend that you go through our online learning library and learn more about data science, both the concepts and the specific practices strongly associated with data mining. And learning more about data science will make you better at data mining tasks. In particular, you may want to place some special emphasis on machine learning algorithms. We've covered several of those in this course, things like the neural networks, but you're going to want to look at more of these so you have a wide range of tools to help you when you're working on your data mining projects. And of course, you want to think about the actual programming tools that you use. Python and R are the two most common tools within data mining, and we have versions of this course for both Python and R. You finish watching one, I strongly recommend you take a look at the other so you have a more diverse range of opportunities ahead of you. And then finally, because data mining usually happens within an applied and frequently commercial or organizational context, it's a good idea to go and learn more about how businesses are run, about the questions that are important to them, and how value can be derived from the insights that data mining gives you. Now, apart from that, I'm actually going to encourage you to get creative. We've been talking about a lot of technical details, but there's a lot of room for originality and for experimentation. Try different data sets. Try changing some of the commands. See what happens. Bring in something new. See what insights you can find through these iterations, through these variations, you may surprise yourself. If you want some good inspiration, I recommend that you go try meeting with user groups and meetup groups, either in person or online. The kind of social networking and the spontaneous influences you can get from other people can be enormous help in finding new and creative ways to work with data in data mining. But most importantly, get your tools together, get going, and see where it takes you. You'll be surprised by what you find. Thanks so much for joining me, and best of luck in your data mining projects.